In the silent rhythm of our universe, there exists a force so constant, so fundamental, that we barely notice its omnipresence. It is not felt directly, like wind against skin or water's gentle flow. Rather, it is the invisible architect of all we know, gravity, the subtle force that keeps your feet planted on the ground, the clouds suspended in air, and our planet faithfully circling its star. Gravity is not merely a force of attraction. It is the very fabric upon which our existence is written. The reason oceans have shores, mountains have peaks, and stars have planets. It guides raindrops to Earth, holds galaxies in their spiraling dance, and gives weight to every moment of our lives. From the grandest scales of cosmic architecture to the smallest particles of matter, gravity weaves through existence with quiet persistence. It shapes the curve of space-time itself, bending light around massive objects and slowing time near dense bodies. Though it may be the weakest of nature's four fundamental forces, its reach is infinite, its influence universal. Our bodies have evolved within its constant embrace. Our blood flows according to its pull. Our bones grow against its resistance. Even our sense of balance, of up and down, exists only because gravity provides the reference point. It is written into our biology, our architecture, our language. But what if, in a moment that defies all known physics, this fundamental force simply ceased to exist? What if gravity, the silent supporter of all structure in our universe, suddenly stopped working? Imagine waking on an ordinary morning. The sun rises as it always has. Birds sing outside your window. A cup of coffee steams on your table. And then, in an instant beyond explanation, everything changes. The coffee lifts from its cup. Suspended in mid-air, the birds halt their flight, suddenly untethered. And you, without warning, begin to drift from your chair. This is the moment gravity vanishes. A moment impossible by every law of physics we know, yet illuminating in what it reveals about our dependence on this universal force. Gravity has been with us since the beginning. In the earliest moments after the Big Bang, as matter condensed from energy and the first particles formed, gravity was there, guiding the cosmic dance. It pulled hydrogen atoms together to form the first stars. It shaped the galaxies, those vast islands of stars spinning in the void. It orchestrated the birth of our solar system from a cloud of dust and gas, compressing matter until nuclear fusion ignited our sun and spinning the leftover material into planets, moons, asteroids, and comets. And gravity has been with life since its first appearance. It gave direction to the growth of plants, reaching upward against its pull. It shaped the bodies of animals, building bones and muscles strong enough to move against its constant resistance. It kept our atmosphere wrapped around our planet, protecting the fragile experiment of life from the harsh vacuum of space and the deadly radiation of our star. We take for granted how gravity organizes our world, the way it holds down our atmosphere, creating the air pressure our bodies need, the way it guides rivers to the sea, the way it keeps our planet spinning at a stable rate, giving us the reliable rhythm of days and nights, seasons and years. In human history, gravity has been both obstacle and opportunity. We have dreamed of flight precisely because gravity makes it so difficult. We have built ever taller structures as challenges to its limiting force. And in our most ambitious moments, we have broken free of Earth's gravitational well to explore the space beyond, even while remaining forever bound to gravity's universal law. Consider for a moment the profound influence gravity exerts on our daily lives. In ways so commonplace, we scarcely notice them. The simple act of walking, that fundamental human locomotion, is a continuous negotiation with gravity. Each step involves falling forward and catching ourselves, a controlled surrender to and resistance against Earth's pull. Our sense of weight, of substance and presence in the world, comes from gravity's constant embrace. The seasons themselves, those rhythmic changes that have guided human activity for millennia, depend on our planet's tilted axis as it orbits the sun, a dance choreographed by gravitational forces. The tides that have shaped coastlines and influenced maritime cultures throughout history rise and fall to gravity's patient rhythm as the moon orbits our world. Even our language and thought are permeated with gravity's influence. We speak of being grounded, of rising to occasions, or falling from grace. Our concepts of hierarchy often follow a vertical arrangement, with importance ascending upward against gravity's pull. Our religions place heavens above and underworlds below, a spatial orientation that reflects our most basic physical experience of the world. Gravity shapes the very sound of music. The tension and release in melody and harmony mirror the physical sensation of lifting something against gravity's pull and then letting it fall. The downbeat that anchors rhythm reflects the natural emphasis we feel as our feet strike the ground when walking or dancing. In the cosmos beyond Earth, gravity reveals itself as the great storyteller, writing the narrative of universal evolution. It creates the conditions where atoms can join to form molecules, where clouds of gas can collapse to form stars, where the debris around young stars can gather into planets. Without gravity, the universe would be a formless fog of particles, never coalescing into structures complex enough to harbor life. Gravity is the force that allows complexity to emerge from simplicity. By bringing matter together against the universe's tendency toward expansion and dissolution, it creates pockets where energy can flow, where chemistry can become intricate, where biology can evolve. It is the counterforce to entropy, temporarily creating islands of order in a sea of increasing disorder. What would happen in those first bewildering seconds? How would Earth respond as its binding force disappeared? What fate would befall our solar system, our galaxy, the universe itself? And could anything, anyone, possibly survive in a cosmos suddenly liberated from gravity's embrace? This is not a story of scientific possibility, for as far as we understand, gravity cannot simply switch off. Rather, it is a thought experiment that reveals just how profoundly this invisible force shapes everything we know and everything we are. So settle in, close your eyes if you wish, and imagine with us a universe about to lose its oldest, most faithful companion, a world about to drift apart. What if gravity suddenly stopped working? Since the dawn of human consciousness, we have known that things fall. The apple drops from the tree, the water flows downhill, the stars hang in the sky while we remain earthbound. But understanding why these things happen took thousands of years of human thought. Our story begins in 1687, in the garden of a mathematician in Lincolnshire, England. As the tale goes, Isaac Newton was sitting under an apple tree when he watched an apple fall straight to the ground. In that moment, a question formed in his mind. Why did the apple fall downward and not sideways or upward? What invisible force guided its path? Newton reasoned that some attraction must exist between the earth and the apple, a force pulling them together. And, in a leap of insight that would change our understanding of the universe forever, he wondered if this same force might extend beyond our world. Could it be the very same force that keeps the moon in orbit around Earth? Could this force reach all the way to the planets, explaining their dance around the sun? The answer, he discovered, was yes. Newton formulated his universal law of gravitation, which states that every object with mass attracts every other object with mass. The strength of this attraction depends on two things. First, how massive the objects are. Second, how far apart they are. The greater the mass, the stronger the pull. The greater the distance, the weaker the pull. This inverse square relationship means that if you double the distance between two objects, the gravitational force between them becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. This explains why we feel Earth's gravity strongly but don't feel the gravitational pull of distant stars and planets, despite their enormous mass. Before Newton, many brilliant minds had pondered the question of falling objects and celestial motion. The ancient Greeks believed that celestial bodies moved in perfect circles, governed by different laws than earthly objects. Aristotle taught that heavy objects fell faster than lighter ones, an idea that would persist for nearly 2,000 years, until Galileo Galilei demonstrated that all objects, regardless of mass, fall at the same rate in the absence of air resistance. Galileo's famous experiment, where he allegedly dropped objects of different weights from the Leaning Tower of Pisa, challenged centuries of accepted wisdom. Though the tower story may be apocryphal, his careful measurements of balls rolling down inclined planes revealed that falling objects accelerate at a constant rate. This crucial insight paved the way for Newton by suggesting that a single mathematical law might describe all falling motion. Meanwhile, the heavens were being remapped. Nicolaus Copernicus had proposed that Earth orbited the Sun, not the other way around. Johannes Kepler had discovered that planets move in ellipses, not circles, and had formulated 3 mathematical laws describing their motion. But nobody had connected these celestial mechanics with the everyday experience of earthly gravity until Newton. Newton's breakthrough was realizing that the force making an apple fall and the force keeping the moon in orbit were identical. The math worked perfectly. He calculated that the moon's orbit could be explained precisely by the same gravitational attraction that pulls objects to Earth, adjusted for the moon's greater distance. This unification of earthly and celestial physics was revolutionary, collapsing the ancient division between the heavens and Earth into a single natural law. Newton's equations worked brilliantly. They explained the motions of planets with unprecedented accuracy. They allowed astronomers to predict the positions of celestial bodies. They even led to the discovery of Neptune, found by calculating where an unseen planet must be to cause observed disturbances in Uranus' orbit. For over 2 centuries, Newton's view of gravity as a force acting across empty space served as the foundation of physics. But there was a problem. Newton himself recognized it. How exactly did this force transmit across the vacuum of space? What was the mechanism by which 2 distant objects could pull on each other without any physical connection between them? Newton had no answer, famously declaring, "I frame no hypotheses." This action at a distance troubled many of Newton's contemporaries. How could objects influence each other without something connecting them? Various solutions were proposed. Perhaps space was filled with an invisible substance, an ether, that transmitted gravitational influence. Perhaps gravity worked through pressure differences in this medium. But none of these explanations satisfied the mathematical precision of Newton's equations or survived experimental testing. For over 2 centuries, this tension remained. Physicists used Newton's laws with spectacular success while remaining uncomfortable with their philosophical implications. The laws worked perfectly in practice, yet their theoretical foundation seemed incomplete. This tension would not be resolved until a young patent clerk in Switzerland, thinking deeply about the nature of light, space, and time, reframed the entire problem. Enter Albert Einstein, more than 200 years later. In 1915, Einstein published his general theory of relativity, which reimagined gravity not as a force pulling objects together, but as a warping of space-time itself. Einstein's journey to this remarkable conclusion began a decade earlier with his special theory of relativity, which showed that space and time were not absolute but relative, varying depending on an observer's motion. This theory successfully unified the laws of mechanics with the laws of electromagnetism, but it did not initially include gravity. Einstein spent the next 10 years grappling with how to incorporate this most fundamental force. His crucial insight came from what he later called the happiest thought of my life. Einstein realized that a person in freefall does not feel their own weight. Someone falling from a roof, if they could ignore the approaching ground and their own fear, would feel weightless during the fall. This equivalence between freefall and weightlessness suggested a deep connection between gravity and acceleration, which became the foundation of general relativity. Imagine space-time as a vast rubber sheet. Place a heavy bowling ball on this sheet, and it creates a depression. Roll a marble near the bowling ball, and the marble will follow a curved path because it is traveling through curved space. This is Einstein's profound insight. Massive objects, like stars and planets, curve the fabric of space-time around them, and other objects moving through that curved space follow paths that appear to be caused by an attractive force. In Einstein's view, Earth is not pulling you down with some mysterious action at a distance. Rather, Earth has created a deep well in space-time, and you are simply following the curvature of that well. When you drop an apple, it falls not because Earth is pulling it, but because it is following the straightest possible path through curved space-time. This conceptual shift, replacing a mysterious attracting force with the geometry of a curved manifold, represents one of the most beautiful intellectual achievements in human history. It resolved the ancient problem of action at a distance by eliminating the need for action altogether. Objects influenced each other not by reaching across space, but by changing the very space in which other objects moved. This geometric view of gravity explained phenomena that Newton's theory could not, such as the precise orbit of Mercury around the Sun. For decades, astronomers had observed that Mercury's orbit shifted slightly with each revolution, a phenomenon called perihelion precession. Most of this shift could be explained by the gravitational influence of other planets, but a small discrepancy remained. Einstein's equations accounted for this discrepancy exactly, providing one of the first confirmations of general relativity. It also predicted new phenomena that Newton could never have imagined. Light, which has no mass, should also follow the curvature of space-time. This prediction was dramatically confirmed during a solar eclipse in 1919, when starlight was observed bending around the Sun, exactly as Einstein had calculated. This observation made Einstein world famous overnight, transforming him from an obscure physicist into a global celebrity. The eclipse experiment, led by Sir Arthur Eddington, was a remarkable scientific and human achievement. Conducted just months after the end of World War I, it represented a British scientist confirming the theory of a German physicist, demonstrating that scientific truth transcended national rivalries and war. When asked what he would have thought if the observations had not confirmed his theory, Einstein reportedly replied, "Then I would have been sorry for the dear Lord. The theory is correct." Einstein further predicted that massive objects could warp space-time so severely that not even light could escape their gravity. These theoretical objects, which we now call black holes, have since been observed throughout our galaxy and beyond. At their center lies a singularity, a point where matter is compressed to infinite density and space-time is infinitely curved. For decades after Einstein proposed their existence, black holes remained theoretical curiosities. Many scientists, including Einstein himself, doubted whether these extreme objects could actually form in nature. But as observational astronomy advanced, evidence mounted. Strange radio sources, X-ray emissions from binary star systems, and the bizarre behaviors of stars near the center of our galaxy all pointed to the existence of these space-time aberrations. In 2019, the Event Horizon Telescope captured the first image of a black hole, confirming once again the extraordinary accuracy of Einstein's theory. This black hole, located at the center of galaxy Messier 87, appears as a dark circle surrounded by a ring of light, exactly as predicted by general relativity. This image, created by combining data from radio telescopes across Earth to form a virtual telescope the size of our planet, represents one of the most remarkable achievements in the history of astronomy. Another prediction of Einstein's theory was the existence of gravitational waves, ripples in space-time, that propagate at the speed of light. These waves, created when massive objects accelerate, are incredibly subtle, changing the distance between objects by less than the width of an atomic nucleus as they pass. For nearly a century, they remain beyond our ability to detect, leading some physicists to question whether they existed at all. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the first gravitational wave. It came from the collision of two black holes over 1 billion light-years away, an event so cataclysmic that in its final moments it released more energy than all the stars in the observable universe combined. Yet by the time these waves reached Earth, they altered the distance between LIGO's mirrors by just 1/10,000th the width of a proton. This detection opened an entirely new field of gravitational wave astronomy, allowing us to observe events that emit no light. What makes gravity truly special among the 4 fundamental forces is its unlimited range. While the strong and weak nuclear forces operate only at subatomic distances, and the electromagnetic force weakens over distance, gravity reaches across the entire universe. It is also strictly attractive. Unlike electric charges, which can either attract or repel, masses only attract other masses. Yet for all its cosmic importance, gravity is astonishingly weak. The electromagnetic force between two protons is about 10 to the power of 36 times stronger than the gravitational force between them. This weakness is why you can pick up a small object with a magnet, overcoming the gravitational pull of the entire Earth. It's also why we can jump, temporarily defying the gravitational attraction of our entire planet. To put this weakness in perspective, consider that a small toy magnet can lift a paperclip, overcoming the gravitational pull of the entire Earth. The electromagnetic force in that tiny magnet overwhelms the gravitational force of a planet massing over 6 billion trillion kilograms. This disparity in strength between gravity and the other forces represents one of the great puzzles in physics, known as the hierarchy problem. Gravity's weakness may seem like a design flaw, but it is probably essential for our existence. If gravity were much stronger, stars would burn through their fuel far more quickly, and planets might be crushed by their own weight. The delicate balance of forces that allows complex structures like galaxies, stars, planets, and ultimately life to exist depends on gravity being precisely as weak as it is. This fine-tuning has led some to invoke the anthropic principle, the idea that we observe a universe with these particular properties, precisely because these are the properties that allow observers like us to exist. In a universe with stronger gravity, stars might burn out before life could evolve. In a universe with weaker gravity, matter might never coalesce into stars and planets at all. We find ourselves in a universe with gravity just right for complexity, because only such a universe could produce beings capable of measuring gravity. Despite our mathematical descriptions of how gravity works, we still don't fully understand its nature at the quantum level. While the other three fundamental forces have been successfully described in terms of particle exchange, attempts to quantize gravity and unify it with quantum mechanics have proven enormously challenging. Theoretical physicists continue to pursue a theory of quantum gravity through approaches like string theory and loop quantum gravity. The problem lies in the fundamentally different natures of general relativity and quantum mechanics. General relativity describes gravity as the curvature of smooth, continuous space-time, while quantum mechanics describes the other forces as the exchange of discrete particles in a probabilistic framework. These frameworks have proven remarkably difficult to reconcile. String theory attempts to solve this problem by replacing point particles with tiny one-dimensional strings, whose vibrations manifest as different particles. In this framework, the graviton, the hypothetical particle that carries the gravitational force, emerges as a particular vibrational mode of these strings. Loop quantum gravity, meanwhile, proposes that space-time itself has a discrete, quantum structure at the smallest scales, rather like pixels in a digital image. For now, we live with two powerful but incompatible descriptions of gravity. At cosmic scales, Einstein's general relativity reigns supreme, describing how massive objects warp space-time. At quantum scales, we still lack a complete theory. This divide represents one of the greatest unsolved problems in modern physics. In our everyday lives, we experience gravity as the most familiar of forces. It gives us weight, grounds us to Earth, and provides the backdrop against which we move through the world. It shapes our bones, our blood flow, our sense of balance, yet it remains in many ways the most mysterious of nature's fundamental forces. The influence of gravity extends far beyond keeping our feet on the ground. It creates the tides, as the moon and sun pull on Earth's oceans. The rhythmic rise and fall of sea levels that has shaped coastlines and influenced human history for millennia is simply the result of gravitational attraction between celestial bodies. The tides have influenced human culture since prehistory. Ancient civilizations used tidal patterns to plan fishing and coastal navigation. Tidal pools created unique ecosystems that provided early humans with reliable food sources. Even today, tidal energy represents a promising renewable resource, harnessing the gravitational dance of Earth, Moon, and Sun to generate electricity. Gravity governs the weather patterns that bring rain to our crops and wind to our sails. It shapes the convection currents in our atmosphere and oceans, driving the global circulation that distributes heat from the equator toward the poles. Without gravity, there would be no weather, no climate, no atmospheric pressure. The everyday experience of air pressure, the weight of the atmosphere pressing against our bodies, is gravity's work. At sea level, each square inch of your body bears the weight of 14.7 pounds of air, a pressure we have evolved to find comfortable. As you climb a mountain, this pressure decreases with altitude as there is less air above you, a direct consequence of gravity's pull on air molecules. Gravity also dictates the structure of our planet itself. The weight of rock pressing down creates the incredible pressures that transform carbon into diamond deep beneath the Earth's surface. The pull of gravity drives the convection currents in the mantle that move tectonic plates, build mountains, and trigger earthquakes and volcanoes. Our planet is round because gravity pulls equally in all directions, shaping large objects into spheres. On a cosmic scale, gravity is the great architect. In the early universe, tiny fluctuations in the density of matter were amplified by gravity, pulling more and more material together to form the first stars and galaxies. Gravity caused gas clouds to collapse, heating up until nuclear fusion ignited, giving birth to stars. It gathered leftover material around these stars into planets and moons. Gravity continues to shape the cosmos today. It causes galaxies to rotate, their outer arms moving more slowly than Newton's laws would predict, giving us evidence of the existence of dark matter. It bends light around massive objects, creating beautiful cosmic mirages called gravitational lenses that allow astronomers to see galaxies that would otherwise be hidden from view. Gravitational lensing has become one of astronomy's most powerful tools. By studying how light bends around massive galaxy clusters, scientists can map the distribution of dark matter, the mysterious substance that appears to make up about 85% of the matter in the universe. Lensing also magnifies distant objects, allowing us to see galaxies so far away that they would otherwise be beyond the reach of our most powerful telescopes. In the largest structures of the universe, gravity organizes galaxies into clusters, and clusters into superclusters, connected by vast filaments of matter with enormous voids between them. This cosmic web, stretching across billions of light years, owes its architecture to the relentless pull of gravity over cosmic time. Even time itself is not immune to gravity's influence. Einstein showed that time passes more slowly in stronger gravitational fields, a phenomenon called gravitational time dilation. This is not just a theoretical curiosity. The atomic clocks in GPS satellites must be adjusted to account for the fact that time passes slightly faster in orbit than it does on Earth's surface. Without this correction, GPS navigation would quickly become inaccurate. This relativistic effect applies to all clocks, mechanical or biological. If you lived your entire life on a planet with stronger gravity than Earth, you would age more slowly than your twin living on Earth, though you would not notice any difference in your subjective experience of time. Your biological processes, your heartbeat, your thoughts would all proceed at what feels to you like a normal pace. Only when the twins reunited would the age difference become apparent. The extreme version of this time dilation occurs near black holes, where time can slow to a crawl compared to distant observers. If you could somehow hover just outside the event horizon of a black hole, you might witness the entire future history of the universe play out before you in what would seem to you like moments. Gravity also affects light, causing it to lose energy as it climbs out of a gravitational well. This gravitational redshift means that light from very massive objects appears redder than it would otherwise. The most distant galaxies we observe are redshifted not just because of the expansion of the universe, but also because of the gravitational wells they had to climb out of to reach us. In Einstein's relativity, gravity and acceleration are equivalent. This principle, known as the equivalence principle, means that the effects of gravity cannot be distinguished from the effects of acceleration. If you were in a sealed room accelerating upward at 9.8 meters per second squared, the experience would be identical to standing in Earth's gravity. This deep connection between gravity and acceleration is at the heart of our modern understanding of space-time. The equivalence principle has been tested with extraordinary precision. The Yotvos experiments, begun in the late 19th century and refined over decades, confirm that objects of different compositions fall at exactly the same rate, a key prediction of the principle. More recently, satellite missions like Microscope have tested the principle to parts per trillion, finding no violations. Scientists continue to test the limits of our understanding of gravity. Experiments like LIGO, the Laser Interferometer Gravitational Wave Observatory, have detected ripples in space-time called gravitational waves, created by cataclysmic events like the collision of black holes. These observations, first made in 2015, opened an entirely new way of observing the universe, allowing us to detect events that emit no light. The quest to reconcile gravity with quantum mechanics remains one of the greatest challenges in theoretical physics. Various approaches, like string theory, loop quantum gravity, and causal set theory, each offer potential paths forward, but none has yet provided a complete and testable theory of quantum gravity. Some theories suggest that gravity might leak into extra dimensions beyond the three spatial dimensions we experience, explaining its comparative weakness. Others propose that gravity is not a fundamental force at all, but an emergent property arising from the behavior of quantum fields, much as temperature emerges from the collective motion of atoms and molecules. This incomplete understanding of gravity at the quantum level does not diminish the extraordinary accuracy of Einstein's general relativity in describing gravity at larger scales. From the precise orbit of Mercury to the bending of light around the Sun, from the synchronization of GPS satellites to the detection of gravitational waves, general relativity has passed every experimental test with flying colors. As we look to the future, gravity's mysteries continue to drive scientific exploration. Advanced gravitational wave observatories will detect ever more subtle ripples in spacetime, potentially even those left over from the Big Bang itself. Space-based experiments will test the equivalence principle with unprecedented precision. And perhaps, someday, a breakthrough in theoretical physics will finally unite gravity with the quantum world, completing the revolution that Newton began under his apple tree. Now, with this understanding of gravity in mind, what would happen if this most constant companion suddenly vanished? How would the universe respond if, in defiance of everything we know about physics, gravity simply stopped working? Imagine an ordinary day. Morning light filters through your window, birds sing outside, a routine so familiar you hardly notice it. But today, something impossible is about to happen. In the next moment, the fundamental force that has shaped our universe since its beginning will simply cease to exist. The change would be instantaneous and unmistakable. In that first fraction of a second, you would feel a profound lightness, as if some ever-present hand had suddenly released its gentle pressure on your body. The sensation would be unlike anything you have ever experienced. Not like swimming, where water still provides resistance. Not like skydiving, where air rushes past you. Not even like the brief weightlessness of a roller coaster cresting a hill. This would be true weightlessness. Your body, which has evolved for billions of years in gravity's embrace, would suddenly find itself without the force that has shaped every aspect of its design. Blood that normally pools slightly in your lower extremities would redistribute throughout your body. Your sense of balance, dependent on the fluid in your inner ear responding to gravitational pull, would become confused. The vestibular system in your inner ear, which has spent every moment of your life tracking your orientation relative to Earth's gravitational field, would suddenly receive conflicting signals. The tiny calcium crystals called otoliths that normally press down on sensory hair cells would float freely, sending chaotic impulses to your brain. This sensory confusion would likely cause immediate dizziness, nausea, and spatial disorientation, similar to but more intense than motion sickness. Your cardiovascular system, exquisitely tuned to pump blood against gravity's downward pull, would suddenly find itself overcompensating. Blood pressure would increase in your head and decrease in your lower body. The baroreceptors in your blood vessels, which help regulate blood pressure, would trigger emergency responses designed for situations they were never meant to address. Your heart might slow temporarily as your body misinterpreted the blood pressure changes as dangerous hypertension. In that first moment, you might not even move. Inertia, the tendency of objects to maintain their current state of motion, would still exist. The laws of motion, discovered by Newton, would still apply. Only gravity would be gone. So if you were sitting in a chair, you would remain there briefly, though you would feel no pressure against the seat. But any small movement, even the expansion of your chest as you breathe, would set you adrift. With no force pulling you toward Earth, the slightest push against any surface would send you floating away from it. If you were outdoors, even a gentle breeze would be enough to lift you from the ground. The micro-movements you make constantly without awareness, the small adjustments of muscles that maintain your posture, would suddenly translate into random motion. A slight tilt of your head might send you slowly rotating. The force of blood pumping through your arteries might cause a barely perceptible drift. Even the air expelled from your lungs as you exhale would provide enough thrust to set you moving in the opposite direction. All around you, similar scenes would unfold. People would begin to float upward, slowly at first, like balloons released by careless hands. Cars would lose contact with the road, their momentum carrying them forward in straight lines until they collided with floating obstacles. Birds in mid-flight would continue on their trajectories but would find their wings suddenly ineffective in a world where up and down have lost their meaning. In homes around the world, everyday objects would become untethered. The contents of cups would form perfect spheres, floating away from their containers. Shower water would break into glistening orbs, suspended in bathroom air. Sleeping pets would wake in confusion as they drifted from their beds. Children might laugh with delight, at least initially, as their toys floated alongside them. The mundane would become magical, moments before turning deadly. Those in elevators would find themselves in a particularly strange situation. No longer pulled downward, yet contained within a small space, they might float freely within the cab. If the elevator were in motion when gravity disappeared, its machinery would continue pulling the cab upward or letting it descend through momentum, but passengers would float freely inside, potentially colliding with the ceiling or walls as the elevator moved around them. The atmosphere that blankets our planet would begin to disperse. Air, no longer bound by Earth's gravitational pull, would start expanding outward in all directions. This would not be instant, as air molecules would still collide with each other, creating pressure. But this pressure would now push the atmosphere ever outward into the vacuum of space. The physics of this atmospheric expansion would be complex. Air pressure at sea level is about 14.7 pounds per square inch, equivalent to the weight of the entire column of air above that point. With gravity gone, this pressure would drive expansion, but not uniformly. The rate would depend on temperature, with warmer air expanding more rapidly than cooler air. The atmosphere would begin to stratify based on molecular weight, with heavier gases like carbon dioxide expanding more slowly than lighter ones like hydrogen. In a remarkable twist, you would not immediately notice the air thinning. Your immediate surroundings would maintain adequate pressure for minutes to hours, as air disperses relatively slowly. But the expansion would be accelerating. Without gravity, there is nothing to keep our precious envelope of air hugging the Earth. This decompression would proceed logarithmically, meaning the rate of pressure loss would increase over time. Within minutes, those at higher elevations would begin to experience altitude sickness as oxygen levels dropped. Within perhaps an hour, even those at sea level would notice difficulty breathing. The partial pressure of oxygen in your lungs would fall below the level needed to saturate your hemoglobin, gradually reducing your cognitive function and physical capabilities before you lost consciousness. Water would behave even more strangely. In ponds, lakes, and oceans, surface tension would momentarily hold some water together in giant globules. But as these floating masses collided with objects or experienced internal ripples, they would break apart into countless smaller spheres of different sizes. Rivers would cease to flow downhill, since downhill would no longer exist. Instead, they would fragment into floating balls of water, creating surreal suspended sculptures in the air. Surface tension, a property arising from the cohesive forces between water molecules, would now be the dominant force shaping water's behavior. A floating sphere represents the minimum surface area for a given volume, which is why water droplets form round shapes in the absence of other forces. In our scenario, these spheres would range from microscopic to potentially miles across for briefly intact portions of oceans. The physics of these water spheres would be fascinating. Within each one, hydrostatic pressure would equalize, creating uniform pressure throughout, regardless of size. Impurities and dissolved substances would remain evenly distributed initially, though over time they might separate according to density. Fish and other aquatic life might find themselves trapped inside these spheres, alive but in an environment growing increasingly alien by the minute. Rain would stop falling. Droplets formed in clouds would remain suspended where they were or drift with air currents. Indeed, weather as we know it would end in that instant. Without gravity to create convection currents, without the weight of cold air pushing down and displacing warm air upward, the machinery of our planet's atmospheric circulation would grind to a halt. Cloud formation, which depends on warm air rising until it cools enough for water vapor to condense, would cease. Existing clouds would begin to disperse as their water droplets drifted apart. Wind patterns would change dramatically, no longer driven by pressure differentials created by uneven heating of Earth's surface. Instead, the remaining air movements would be dominated by the planet's rotation, the expansion of the atmosphere, and the inertia of previous weather systems. This atmospheric transformation would produce visual effects of haunting beauty. Without gravity-driven convection, pollution would no longer concentrate in lower layers of the atmosphere. Dust and particulates would disperse more evenly, potentially creating unusual optical effects as sunlight filtered through the changing medium. For a brief time, before the sky darkened to black, observers might witness spectacular light shows as sunlight refracted through water droplets suspended at unusual heights and orientations. More alarming would be the behavior of the ground beneath your feet. Soil and loose rock, no longer compacted by gravitational pressure and their own weight, would begin to lose cohesion. Landslides would occur, not downward but outward, as compressed soil and rock expanded like a spring suddenly released. Dust would lift from every surface, creating a thickening haze. The soil beneath our feet is normally compressed by both its own weight and the weight of everything above it. Soil at just 1 foot depth typically experiences pressure of about 5 pounds per square inch from the weight of soil above it. When this pressure suddenly disappears, the soil would expand like a compressed sponge released. The expansion would vary by soil type, with clay soils potentially expanding more than sandy ones due to their greater compressibility. Geological formations under extreme pressure would react more dramatically. In deep mines and caves, rock walls might shatter explosively as the pressure containing them vanished. Oil and natural gas deposits, normally held in place by capillary forces and overlying rock pressure, might seep upward through newly created fissures. Underground aquifers would no longer flow toward areas of lower elevation, instead forming subsurface bubbles that would expand against the surrounding soil and rock. Plant life would respond oddly to the sudden change. Trees, which have grown all their lives against the pull of gravity, developing sturdy trunks and branches to support their weight, would find themselves suddenly over-engineered for a weightless environment. Some might actually spring upward slightly, as tensions within their woody tissues suddenly find themselves unopposed. But unlike animals, plants would not immediately float away. Their roots, intertwined with soil and rock, would keep them temporarily anchored, even as the soil itself began to loosen. The biology of plants would be fundamentally disrupted. Plant growth hormones called auxins, which concentrate on the downward side of stems and roots to guide their directional growth, would distribute evenly without gravity. The complex mechanisms that trees use to transport water from roots to leaves, which rely partially on gravitational potential energy, would fail. Photosynthesis might continue briefly, but the entire evolved architecture of plant life would suddenly find itself solving problems that no longer existed. Seeds and pollen, normally dispersed by falling or being carried by wind whose patterns are shaped by gravity, would float aimlessly. Flowers, typically oriented to maximize light capture or to attract pollinators from above or below, would lose their directional significance. The entire intricate dance of plant ecology, fine-tuned over hundreds of millions of years to gravitational conditions, would stumble to a confused halt. Buildings and structures would face a complex fate. They would not immediately collapse or fly apart, as the chemical bonds holding their materials together would still exist. Gravity is not what holds atoms or molecules together. However, structures designed with gravity's constant pull in mind would suddenly find themselves dealing with new stresses. Skyscrapers, for instance, are designed to channel their enormous weight down through their frames to their foundations. Without this downward force, the tensions and compressions within their structures would begin to resolve in unpredictable ways. Consider how buildings are constructed. Compression members like columns and load-bearing walls are designed to resist the downward force of gravity. Tension members like cables in suspension bridges or steel beams in modern skyscrapers are designed to support loads that would otherwise fall. When gravity vanishes, compression members would suddenly be over-engineered, while tension members would go slack. The balance of forces that keeps our structures stable would be fundamentally altered. The materials themselves would behave differently too. Concrete, for example, is strongest under compression and weakest under tension. Steel has high tensile strength. Engineers combine these materials to create reinforced concrete that handles both forces well. Without gravity, the compressive forces would disappear, potentially causing concrete to crack as embedded steel reinforcement shifted. Glass windows, no longer compressed within their frames, might pop out. Nails and screws, designed to resist gravitational pull, might lose their grip. Below the surface, Earth's interior would undergo its own transformation. Our planet has what scientists call hydrostatic equilibrium, a balance between gravitational compression pulling everything toward the center and pressure pushing outward. Without gravity, this balance would be broken. The immense pressure of the inner layers, no longer contained by gravitational force, would start to push the entire planet outward like a coiled spring being released. This expansion would begin at the center and propagate outward, though it would take time to reach the surface. The pressure at Earth's center is estimated at about 3.6 million atmospheres. Under normal conditions, this extreme pressure compresses iron in the inner core to a density greater than it would have at the surface, despite temperatures comparable to the sun's surface. When gravity disappears, this compressed material would begin to expand dramatically. The solid inner core would likely liquefy as pressure dropped, while the already liquid outer core would expand even more rapidly. The mantle, a layer of silicate rock nearly 2,000 miles thick, exists in a semi-solid state, flowing very slowly under normal conditions. Without gravitational containment, its behavior would change radically. Regions of higher temperature and pressure would expand more rapidly, creating complex convection patterns unrelated to their previous gravity-driven flow. The magma chambers feeding volcanoes would no longer be pressurized by the weight of overlying rock, potentially leading to massive simultaneous eruptions worldwide as magma expanded outward. Meanwhile, Earth's rotation would continue. Our planet spins at about 1,000 miles per hour at the equator. Without gravity binding things to the surface, this rotation would begin to fling loose objects outward, like a spinning merry-go-round with no safety bar. This effect would be strongest at the equator and negligible at the poles. The initial effect would be subtle, but would compound as other forces loosened the Earth's structure. This centrifugal effect would create a strange geographical disparity in the immediate aftermath of gravity's disappearance. Those near the equator would experience a slight outward pull perpendicular to the Earth's axis of rotation. Those at mid-latitudes would feel a weaker effect at an angle to the surface. Those near the poles would feel almost no centrifugal effect. This would create different trajectories for floating objects depending on their latitude, adding another layer of complexity to the unfolding chaos. What about the Moon? Its orbit around Earth is a constant freefall, with the Moon's inertia balancing Earth's gravitational pull to create a stable elliptical path. The moment gravity disappeared, the Moon would continue moving tangentially to its previous orbit, essentially flying off in a straight line into space at about 2,230 miles per hour. The Moon's departure would create no dramatic visual effects beyond its gradual receding from view. There would be no atmospheric or tidal consequences, as these effects would already be negated by gravity's disappearance. However, the psychological impact of watching our celestial companion abandon us might be profound for any observers who maintained a view of the sky long enough to notice. The Moon, humanity's constant companion throughout our entire evolutionary history, would become just another abandoning star in an increasingly alien sky. The effects on technology would be equally profound. Satellites in orbit, no longer bound by Earth's gravitational pull, would shoot off in straight lines tangent to their former orbits. The International Space Station would drift away from Earth, though the astronauts inside might be better prepared than most for the sudden onset of weightlessness throughout the universe. Our entire technological infrastructure is designed with gravity as a fundamental assumption. Plumbing systems rely on gravity to move water and waste. Cooling systems in electronics use convection, which requires gravity to function. Internal combustion engines depend on fuel being delivered to their components via gravity-fed systems. Even something as simple as a ballpoint pen relies on gravity to deliver ink to its tip, which is why special space pens had to be developed for astronauts. Our power generation systems would quickly fail. Hydroelectric dams rely on falling water. Without gravity, the water would simply float, generating no power. Fossil fuel and nuclear plants typically use steam turbines that rely on hot steam rising, and cool water falling in a gravity-driven cycle. These would cease functioning almost immediately. Even alternative energy sources would face challenges. Wind turbines would fail as atmospheric circulation patterns collapsed. Solar panels might continue generating electricity longer than other sources, but the grid infrastructure to deliver that electricity would be compromised as transmission towers lost their gravitational anchoring. Battery-powered devices might function temporarily, providing islands of technology in an increasingly primitive world. Combustion itself would change dramatically. Flames, which are normally elongated upward because hot air rises in a gravity field, would form perfect spheres in zero gravity. But as the atmosphere dissipated, oxygen would become scarce, and fires would quickly extinguish. Vehicles with internal combustion engines would sputter and die within minutes to hours. The spherical flames would create unusual hazards before extinguishing. Without the convection currents that normally carry away combustion products and bring in fresh oxygen, flames would consume the oxygen in their immediate vicinity and then suffocate themselves. However, before doing so, they would heat nearby materials more evenly than normal flames, potentially causing unexpected ignitions. Fires that started before gravity disappeared might transform into these strange spherical flames temporarily before going out entirely. For living beings, the initial moments might be filled with confusion or even wonder. The experience of weightlessness, previously available only to astronauts or in brief moments during specialized airplane flights, would suddenly be universal. Some might find it exhilarating to float freely, especially in the first moments before the more catastrophic effects became apparent. Children might adapt more readily than adults to the new conditions, their minds more flexible and less constrained by expectations of how the world should work. Those with experience in three-dimensional environments like scuba divers might find the navigation challenges less overwhelming. Gymnasts, dancers, and others with highly developed body awareness might maintain better control of their movements. But for most, the sudden need to navigate in 3 dimensions without reference points would prove extremely challenging. But human bodies are not designed for prolonged weightlessness, as we know from studies of astronauts on the International Space Station. Without the constant pull of gravity, bones begin to lose calcium, muscles atrophy, and bodily fluids shift upward, causing a host of health problems. Of course, in our scenario, no one would live long enough to experience these chronic effects. Astronauts on long-duration space missions experience bone density loss at a rate of about 1 to 2% per month. Their muscle mass decreases similarly without the constant work of supporting the body against gravity. The heart, no longer having to pump blood against gravitational force, becomes deconditioned. The immune system weakens. Even vision changes as fluid shifts affect pressure within the eyeball. These effects require careful countermeasures during space missions and weeks of rehabilitation upon return to Earth. More immediately concerning would be the simple mechanics of movement. With nothing to push against except floating objects, controlling your motion would become extremely difficult. Each push would send you drifting in the opposite direction, following Newton's third law of motion. Without training in zero-gravity maneuvering, most people would find themselves tumbling helplessly through the air, unable to reach safety. The techniques astronauts use to navigate in zero gravity rely on careful, deliberate movements and stable handholds. In the chaotic environment following gravity's disappearance, with buildings potentially breaking apart and objects floating randomly, these techniques would be difficult to apply. People might instinctively flail their limbs as they tried to swim through the air, but this would only set them tumbling more chaotically. The most effective strategy would be to remain calm and use gentle pushes against stable objects. But panic would make this disciplined approach unlikely for most. Speaking of safety, where would safety even be? As the atmosphere began to disperse, the air would thin and breathing would become increasingly difficult. Temperatures would plummet as air pressure dropped. Without the greenhouse effect of our atmosphere trapping heat, the sunlit side of Earth would eventually cool to far below freezing temperatures. The night side would be even colder. In the vacuum of space, the temperature range between sunlight and shadow is extreme. Objects in direct sunlight can reach over 250 degrees Fahrenheit, while objects in shadow drop to around negative 250 degrees Fahrenheit. As Earth's atmosphere dispersed, this stark thermal contrast would gradually take hold. Surfaces in sunlight would absorb heat without the atmospheric buffer to distribute it, while surfaces in shadow would rapidly radiate their heat into the void. The human situation would be desperate, but perhaps not instantly fatal for everyone. Those who happen to be in sealed environments with oxygen supplies, such as submarines or certain research facilities, might survive the initial hours. But as Earth's structure began to disintegrate around them, even these havens would not last long. The occupants of nuclear submarines might theoretically survive longest. These vessels are designed to operate independently for months, with air regeneration systems, water purification, and nuclear power that doesn't depend on gravity. Similarly, some deep underground bunkers, designed for military or continuity of government purposes, have self-contained environmental systems. But even these would face immediate challenges, as their external pressure equalized with the vacuum forming outside, straining their structural integrity beyond design specifications. Wildlife would face similar challenges. Aquatic creatures might initially fare better than land animals, as their water environments would maintain some integrity through surface tension, forming enormous floating globules. But as these water masses broke apart and began to disperse, marine life would find itself trapped in ever smaller droplets, which would eventually evaporate as they drifted into space. Deep-sea creatures, already adapted to extreme pressure environments, would suffer catastrophically as their surroundings suddenly lost pressure. Swim bladders, which fish use to control buoyancy, would expand rapidly without the counterbalance of water pressure, potentially causing internal injuries. Creatures with air spaces in their bodies, like marine mammals that return to the surface to breathe, would experience effects similar to decompression sickness in human divers who ascend too quickly. Flying creatures would discover that their wings had become useless. Flying works because gravity pulls an animal downward, while its wings generate lift in opposition to that force. With no gravity, birds and insects would find themselves helplessly drifting, unable to control their direction, except by pushing against floating objects they encountered. The most highly adapted flyers, like swifts that spend almost their entire lives on the wing, would be among the most disoriented. Their specialized bodies, evolved for constant aerial motion, would suddenly have no function. Bats, with their sophisticated echolocation, might at least be able to navigate the three-dimensional chaos better than visually oriented birds, but their wings would be equally useless for controlled movement. Perhaps the most visually striking change would be in the sky itself. Sunlight scatters as it passes through our atmosphere, creating the blue daytime sky we know. As the atmosphere dispersed, the sky would darken rapidly, transitioning from blue to deep indigo, and finally to the perfect black of space. Stars would become visible even during the day. The sun would still shine brilliantly, but as a harsh point of light in an otherwise dark sky, much as astronauts see it from space. This transformation would occur progressively from higher to lower altitudes as the atmosphere expanded outward. Those on mountaintops would see the stars emerge in daylight before those at sea level. The edge of space, normally defined as 100 kilometers above sea level at the Kármán line, would effectively descend toward the surface as the atmosphere dispersed. The familiar blue dome that has sheltered humanity throughout our existence would dissolve before our eyes, revealing the cosmic abyss beyond. For those facing the night side of Earth when gravity vanished, the experience would be different. The stars would grow increasingly brilliant as the atmosphere thinned, revealing a universe of piercing light points against absolute darkness. The Milky Way would emerge with unprecedented clarity, a river of light cutting across the sky. The myriad stars normally invisible to the naked eye would bloom into view as the atmospheric veil lifted. The true colors of stars, normally muted by air molecules, would become apparent, with red giants glowing ruby red and hot young stars gleaming blue-white. The planets would appear as bright disks, rather than just points of light. The cosmos would be revealed in all its glory, a final, magnificent display for any observers still capable of witnessing it. The disappearance of gravity would affect not just Earth, but all cosmic structures. The sun would begin to expand, its massive internal pressure no longer contained by gravitational compression. Planets would fly off in straight lines tangent to their former orbits. The entire solar system would unravel in minutes. Though the effects on the sun would begin instantly, the light from these changes would take 8 minutes and 20 seconds to reach Earth, the time it takes light to travel from the sun to our planet. An observer on Earth with an appropriate solar filter might witness the sun's disk begin to expand, and its distinct features like sunspots begin to blur. Eventually, the sun would grow dimmer as its energy spread over a greater area, though this process would take longer than most humans would survive to witness. How long would humans survive in this scenario? For those caught outdoors, loss of consciousness would occur within minutes as the air thinned. Those in sealed environments might last hours to days before their oxygen supplies failed, or their shelters were compromised by the expanding earth beneath them or exposure to the vacuum of space. The human body can remain conscious for only about 15 seconds in a vacuum before the oxygen in the bloodstream is depleted. Contrary to science fiction depictions, exposure to vacuum does not cause the body to explode or freeze instantly. Rather, the primary concern is lack of oxygen to the brain and the formation of gas bubbles in bodily fluids as dissolved gases come out of solution, similar to the bends in scuba diving. Death would follow within minutes if not rescued and repressurized. Those fortunate enough to be inside pressure suits or sealed habitats would face different survival limitations. A standard spacesuit contains about 8 hours of oxygen. Larger habitats might contain days or even weeks of breathable air, but as the Earth itself began to break apart, even these sanctuaries would eventually fail. The mechanical systems that regulate temperature and remove carbon dioxide require stable conditions and regular maintenance, neither of which would be available in the chaotic post-gravity environment. And so, within a remarkably short time, what began as an ordinary day would transform into the end of all terrestrial life as we know it. The disappearance of gravity, that most reliable and underappreciated of forces, would reveal just how perfectly tuned our existence is to its constant presence. But this is only the beginning of our story. To fully understand the consequences of gravity's disappearance, we must look beyond our immediate surroundings to the greater Earth and the cosmic implications of a universe suddenly free from gravity's ordering influence. As the minutes pass in our gravitationless world, the initial floating sensation gives way to more profound and terrifying transformations. The very planet beneath us, held together for 4.5 billion years by gravity, begins to lose its integrity. Earth is about to come undone. Our planet is not a solid ball. It has layers, each with distinct properties. At the center lies the inner core, a solid sphere of mostly iron, roughly 1,500 miles in diameter, and heated to temperatures comparable to the surface of the sun. Surrounding this is the outer core, a churning sea of liquid metal that generates our planet's magnetic field as it flows and rotates. Above that sits the mantle, a layer of hot, slowly flowing rock nearly 2,000 miles thick. And finally, resting atop this structure, like the thin skin of an apple, is the crust, just 25 miles thick at its deepest point. For billions of years, gravity has compressed these layers, creating enormous pressure that increases with depth. At the center of Earth, the pressure exceeds 3.5 million times the atmospheric pressure at sea level. This pressure is what keeps the inner core solid despite its extreme heat. It is what prevents the outer layers from expanding outward. It is what gives our planet its spherical shape and stable structure. When gravity disappears, this pressure remains, but only for an instant. With nothing to contain it, the pent-up force begins to drive Earth apart. The process begins at the center. The inner core, no longer compressed by the weight of the planet above it, starts to melt as its pressure drops. The outer core, already liquid, begins to expand outward. The mantle, composed of rock that behaves like an extremely viscous fluid over geological timescales, begins to flow more rapidly without gravitational constraint. These changes start at the atomic level. Atoms that were once packed tightly together by gravitational pressure now have room to spread out. Chemical bonds remain intact. Gravity doesn't hold molecules together. But the spacing between molecules increases. Materials become less dense. The entire planet begins to expand like a balloon slowly inflating. This expansion is not uniform. Different materials respond to the release of pressure in different ways. Some expand more rapidly than others. Fault lines, already weakened zones in the Earth's crust, become the first places where the expansion becomes visible from the surface. Within hours, new chasms open across the landscape. These are not like conventional earthquake fault lines. They do not follow the boundaries of tectonic plates. Instead, they appear wherever the subsurface materials are expanding at different rates. creating tensile forces that literally tear the crust apart. The oceans, already broken up into countless floating spheres of water, can no longer fill these widening gaps. Instead, the chasms expose the mantle below, which itself is starting to break up. Blobs of semi-solid rock begin to drift upward, no longer held down by their own weight. The once rigid structure of our planet begins to resemble a lava lamp, with materials of different densities passing freely through one another. Volcanoes, which are essentially pressure valves for the Earth's interior, dramatically change their behavior. Without gravity to drive the buoyant rise of magma, traditional eruptions cease. Instead, entire magma chambers simply expand outward in all directions. The distinction between inside Earth and outside Earth begins to blur. Mountains, once formed by the collision of tectonic plates or the upward pressure of rising magma against gravity's constant pull, now begin to crumble in strange ways. They don't collapse downward, but rather expand outward like blooming flowers made of stone. Billions of years of gravitational compression are undone as these mighty structures literally come apart at the seams. The planet swells. Calculations suggest that the initial expansion would be relatively slow, with Earth increasing in diameter by perhaps a few feet per hour, but this rate accelerates as the process continues. By the end of the first day, our planet might be 10% larger in diameter. By the end of the first week, it could double in size. But this expansion is not simply a uniform inflation. As the core pushes outward and different materials expand at different rates, enormous stress patterns develop throughout the planet. These stresses cause the Earth to not merely expand, but to fracture along countless irregular lines. Continent-sized chunks of the crust begin to separate from one another, drifting outward like pieces of a broken shell. Between these separating masses, the mantle becomes exposed to the vacuum of space. Without atmospheric pressure or gravity to constrain it, the exposed mantle material undergoes rapid changes. Some vaporizes instantly, some forms peculiar crystalline structures never before seen in nature. Some simply disintegrates into a fine powder that joins the cloud of debris now surrounding what was once a planet. The Earth's magnetic field, generated by the flowing liquid metal in the outer core, begins to weaken and destabilize. This magnetic field has shielded our planet from harmful solar radiation for billions of years. As it falters, the remaining atmosphere is increasingly bombarded by charged particles from the sun, creating spectacular aurora displays across the entire globe. But few remain to witness this final light show, as the atmosphere itself continues to disperse into space. The expansion is not limited to solid and liquid materials. Gases trapped within the Earth's crust and dissolved in its oceans are released as pressure drops. Methane from the seabed, carbon dioxide from carbonate rocks, and countless other gaseous components join the expanding cloud of Earth's former atmosphere. The planet begins to resemble a comet, surrounded by a growing coma of gas and dust. Life, for the most part, has already ended. Most organisms would have succumbed to the vacuum of space within the first hours. But remarkably, some of Earth's hardiest microorganisms might survive this catastrophe. Certain bacteria, known as extremophiles, can withstand the vacuum of space, extreme radiation, and temperatures near absolute zero. Trapped within chunks of rock or ice now drifting outward from the former Earth, these microorganisms could potentially remain dormant for thousands or even millions of years. The changes to Earth's geography are profound and disorienting. The familiar continents, shaped over billions of years by the slow dance of tectonic plates under gravity's influence, lose all coherence. Africa, Eurasia, the Americas, Australia, Antarctica, these names no longer describe any recognizable features, as the landmasses break apart along new fracture lines that pay no respect to geological history. The great mountain ranges, once the result of tectonic collisions and uplift against gravity, undergo particularly dramatic transformations. The Himalayas, thrust upward over millions of years by the collision of the Indian subcontinent with Asia, now expand outward in all directions. The immense pressure that has built up within these compressed rocks is suddenly released, causing the mountains to burst apart like popcorn in slow motion. Similar scenes unfold at the Alps, the Rockies, the Andes, and other mountain systems around the world. The ocean floors, thinner than the continental crust and under different pressures, respond differently to gravity's disappearance. The vast abyssal plains, already broken up into floating spheres of water, reveal long hidden geological features. Mid-ocean ridges, volcanic zones where new crust is formed as tectonic plates spread apart, suddenly release their pent-up magma all at once, creating explosive outgassing on an unprecedented scale. Deep ocean trenches, where one tectonic plate dives beneath another in a process called subduction, suddenly release the enormous potential energy built up by millions of years of compression. Like massive springs suddenly uncoiled, these zones expel long-buried material back toward the surface in violent upheavals that further contribute to the planet's disintegration. The movement is not just outward. As different parts of the planet expand at different rates, materials begin to move relative to one another, creating a chaotic mixing process. Dense core material pushes outward through the mantle, which in turn breaks through the weakened crust. The Earth's interior, once neatly layered by density under gravity's sorting influence, becomes increasingly homogenized over time. This mixing creates surreal landscapes that would be unrecognizable to human eyes, had any survived to witness them. Metallic blobs from the outer core breach the surface, creating gleaming pools that slowly disperse into space. Diamonds, formed deep within the Earth under immense pressure, suddenly find themselves at or near the surface as the overlying rock expands away. Geological processes that normally take millions of years unfold in days or weeks as the planet literally turns itself inside out. The atmosphere, already beginning to escape into space from the moment gravity disappeared, accelerates its departure as the expanding Earth adds outward momentum to the air molecules. The sky darkens progressively as air density decreases, transitioning through deeper shades of blue until finally becoming the black of space. This process starts at higher altitudes and works its way down, with the air closest to the expanding surface being the last to disperse. The changes to the hydrosphere, Earth's water system, are equally dramatic. Oceans, lakes, and rivers no longer exist as coherent bodies. The floating spheres of water formed in the initial moments after gravity disappeared are now being pushed outward by the expanding Earth beneath them. Many of these spheres collide with debris and break apart into smaller droplets. Others begin to boil away as they are exposed to the vacuum of space, creating a diffuse cloud of water vapor surrounding the disintegrating planet. The ice caps, freed from gravity's compacting force, undergo their own transformation. The massive ice sheets of Antarctica and Greenland, some miles thick, begin to expand and fracture. The compressed air bubbles trapped within ancient ice suddenly expand, causing the ice to become increasingly porous and fragile. Like the rest of the planet, the ice caps eventually fragment into countless floating chunks that join the growing debris field. The creatures living deep underground, from burrowing mammals to colonies of microorganisms miles beneath the surface, might briefly survive longer than surface life. The expanding Earth initially creates voids and spaces where air can remain trapped for a time. But as the fragmentation continues, even these temporary havens are breached, exposing their inhabitants to the vacuum of space. By the end of the first month, Earth as we know it no longer exists. In its place is an expanding cloud of debris, varying in size from dust particles to continent-sized chunks of crust. The densest materials, remnants of the core, form a loose cluster at the center of this cloud. But even this central mass continues to expand and fragment. The debris field follows the Earth's original orbit around the Sun, creating a new asteroid belt of sorts. The larger fragments continue to break apart as their internal pressures seek equilibrium. For years afterward, collisions between these fragments generate smaller and smaller pieces, accelerating the disintegration process. Some fragments, especially those that were blown outward with significant velocity during the initial expansion, escape the solar system entirely. They join the interstellar medium, carrying traces of what was once Earth out into the wider galaxy. If any living microorganisms are trapped within these fragments, they could potentially seed life on distant worlds, an ironic form of panspermia born from our planet's destruction. The water that once covered 70% of Earth's surface undergoes its own remarkable journey. Without gravity, liquid water forms spheres due to surface tension. But exposed to the vacuum of space, these spheres quickly begin to boil at any temperature. This is not the familiar boiling we see in our kitchens. caused by water reaching 100 degrees Celsius. It is boiling caused by low pressure, which allows water molecules to escape their liquid state even at very low temperatures. This boiling is a self-cooling process. As the most energetic water molecules escape as vapor, they carry away heat, causing the remaining liquid to cool rapidly. Eventually, much of Earth's water transitions directly from solid ice to water vapor, without passing through a liquid stage, a process called sublimation. The result is a scattered field of ice chunks, surrounded by an expanding cloud of water vapor. The fate of the Moon is tied to Earth's demise. Having already flown off on a tangent from its orbit in the instant gravity disappeared, the Moon continues on its straight-line path through space. Unaffected by Earth's expansion directly, it nevertheless experiences its own internal changes. Like Earth, the Moon is held together by gravity. Without it, the internal pressure of the lunar core causes the Moon to expand and fracture, though more slowly than Earth due to its smaller size and already partially molten interior. The human artifacts on the lunar surface, footprints of astronauts, flags, and abandoned equipment, initially remain undisturbed. The Moon has no atmosphere to create wind that might erase these marks. But as the lunar surface begins to fracture and expand, even these historic imprints are lost to cosmic history. The artificial satellites orbiting Earth at the moment gravity disappears face a uniquely straightforward fate. These objects, from weather satellites in low Earth orbit to communications satellites in geostationary positions, were all kept in their paths by a balance between gravitational attraction and their own velocity. Without gravity, they simply continue in straight lines tangent to their former orbits, shooting off in all directions like beads from a broken necklace. The International Space Station, that remarkable outpost of humanity in low Earth orbit, similarly departs on a straight-line course. The astronauts aboard, already accustomed to weightlessness, would notice the change primarily through their instruments, which would report a sudden and inexplicable departure from their expected orbit. With no way to return to an Earth that is itself coming apart, they would become unwitting explorers of interstellar space, their habitat gradually failing as supplies run out and systems degrade. Back in what was once Earth's orbit, the debris field continues to evolve. Without gravity to collect the material back into a single body, no new planet will ever form from this cloud. Instead, solar radiation, the solar wind, and the subtle influence of the other planets gradually disperse the smaller particles. Over thousands of years, much of the dust is blown clear of the solar system entirely, while the larger fragments continue their lonely orbit around the Sun. The fate of these fragments depends largely on their size, composition, and new orbits. Some eventually spiral into the Sun, others join existing asteroid populations. A few may impact other planets or their moons. Most simply continue to orbit, gradually wearing down through micrometeorite impacts and radiation exposure, a cosmic graveyard marking where Earth once circled the Sun. The chemical elements that made up Earth continue to exist, merely rearranged. The iron from the core, the silicon and oxygen from the crust, the carbon, hydrogen, and oxygen that made up living things, all these atoms persist, though the structures they once formed are gone. In this sense, Earth is not destroyed but merely dismantled. Its components return to the cosmic inventory from which they originally came. From an astronomical perspective, this catastrophic planetary disintegration would be visible across interstellar distances. The initial expansion would create a temporary increase in Earth's reflectivity, as its greater surface area reflected more sunlight. The cloud of debris might be detectable as an infrared excess around our star, similar to the dust disks seen around other stars that may indicate planetary formation, or in our case, planetary destruction. If distant alien astronomers were observing our solar system during this event, they might initially catalogue it as a peculiar type of nova or an unusual asteroid collision. Only with very precise instruments would they be able to determine that they were witnessing the disappearance of a life-bearing planet. Perhaps the most profound aspect of Earth's disintegration is not the physical process itself, but what it represents. For over 4 billion years, gravity patiently gathered the matter that formed our planet, compressing it, shaping it, and creating conditions where life could emerge and evolve. In mere months, all of that patient work is undone. The elements that once made up our world, our bodies, our civilizations, return to the wider cosmos from which they came. The geological record, that patient chronicle of Earth's history written in stone, is scattered to the cosmic winds. The layered rocks that told the story of ancient seas and long-extinct creatures, the ice cores that preserved samples of atmosphere from hundreds of thousands of years ago, the fossil fuels that represented ancient sunlight stored in the remains of prehistoric forests, all these archives are lost, their stories unraveled along with the planet that housed them. Human creations fare no better than natural ones. Our cities, monuments, and artifacts, from the Great Wall of China to the pyramids of Giza, from undersea cables to satellites, all join the general disintegration. The physical legacy of human civilization, already fragile against the scale of geological time, is utterly erased in this cosmic catastrophe. If any record of humanity survives, it would be only in the form of electromagnetic waves, radio and television broadcasts traveling outward from Earth at the speed of light. Ghostly messengers still propagating long after their source has vanished. The breakup of Earth also releases something less tangible but perhaps more significant, the greatest concentration of organized complexity we know of in the universe, life itself. The intricate biological structures, the ecosystems, the web of relationships between species, the accumulation of genetic information refined by billions of years of evolution, all this organized complexity dissipates, along with the physical planet. The rare phenomenon of life, at least in this corner of the cosmos, suffers a profound setback. In a universe where gravity still existed everywhere else, the matter that was once Earth might eventually recollect, forming a new planet in the same orbit after millions of years. But in our thought experiment, where gravity has ceased to exist throughout the cosmos, no such reformation is possible. The disintegration is permanent and complete. As the centuries pass, the evidence that Earth ever existed grows increasingly sparse. The largest fragments remain, but erosion from micrometeorite impacts gradually smooths their features. Radiation destroys most of the complex organic molecules that might have served as evidence of life. The water vapor and atmospheric gases dissipate into the broader interplanetary medium. After millions of years, all that remains of our once vibrant world are scattered chunks of rock and metal, unrecognizable as pieces of a former planet, silently tracing the orbit where Earth once traveled around the Sun. Our world, our history, our physical existence, all dependent on the constant embrace of gravity, fade into cosmic obscurity. But while Earth itself comes apart in our gravitationless scenario, the effects stretch far beyond our planet. The entire architecture of the solar system, held together by the same force that bound Earth, begins to unravel in equally dramatic fashion. Beyond our disintegrating Earth, the vanishing of gravity wreaks havoc on a far grander scale. Our solar system, that elegant arrangement of planets, moons, asteroids, and comets orbiting our star, begins to unravel with surprising speed. To understand why, we must remember that orbits are essentially a form of perpetual freefall. A planet like Earth stays in orbit around the Sun because the inward pull of gravity precisely balances the planet's tendency to move in a straight line. Every moment, gravity bends what would be a linear path into a curved one, creating the elliptical orbits that planets have followed for billions of years. This delicate balance represents one of nature's most perfect demonstrations of physics in action. For a planet like Earth, traveling at approximately 67,000 miles per hour, the Sun's gravitational attraction provides exactly the right amount of inward acceleration to maintain a nearly circular path. Without this constant bending of the planet's trajectory, Earth would simply continue in whatever direction it was moving at any given moment. It is this precise equilibrium, calculated so elegantly by Johannes Kepler and explained by Isaac Newton, that gives our solar system its clockwork stability and predictable cycles. When gravity disappears, this balance instantly vanishes. Every orbiting body in the solar system continues moving at its current velocity, but now in a perfectly straight line tangent to its former orbit. The carefully arranged clockwork of our solar system transforms into celestial chaos in an instant. The paths taken by these liberated worlds would depend entirely on where each was in its orbit when gravity failed. Some might initially head toward the inner solar system, others directly away from the Sun, while most would follow trajectories somewhere in between. Planets that happen to be at opposite sides of their orbits around the Sun would travel in opposite directions, their paths never to cross again in the vast emptiness of interstellar space. Mercury, the innermost planet, orbits the Sun at an average speed of 30 miles per second. At the moment gravity ceases, it shoots away from the Sun like a stone released from a sling, heading outward into space. Its path would depend on exactly where in its orbit Mercury was when gravity failed, but in any case, the tiny planet would rapidly leave the solar system behind, eventually becoming an interstellar wanderer. Mercury's small size, about 1/3 the diameter of Earth, and its lack of geological activity would allow it to maintain its structure somewhat longer than larger planets. Its heavily cratered surface, resembling our Moon, would remain largely intact as the planet sailed away from its former home. Internal pressure would eventually cause fracturing, but the process would be relatively gradual compared to the violent disintegration of larger worlds. Venus, with its thick atmosphere and volcanic surface, faces a double calamity. Not only does it fly off from its orbit at 22 miles per second, but like Earth, it begins to come apart. The crushing atmospheric pressure on Venus, 92 times greater than Earth's at sea level, suddenly has nothing to contain it. The atmosphere explodes outward in all directions, while the planet itself starts to expand from internal pressure. Within days, Venus would become an expanding cloud of hot gas and fragmented rock. The Venusian atmosphere, a dense layer of carbon dioxide with clouds of sulfuric acid, would expand with explosive force when gravity disappeared. This atmosphere, which maintains surface temperatures of around 860 degrees Fahrenheit, would rapidly cool as it expanded. The optical effect would be striking, with the formerly brilliant point of light that was Venus transforming into a rapidly expanding, gradually dimming cloud. Mars, already a cold, relatively inactive world, would disintegrate more slowly than Earth or Venus. With a smaller mass and less internal heat, the pressure differential driving its expansion would be less dramatic. But its fate would be the same, flying off from its orbit at 15 miles per second, while gradually breaking apart into a dispersing field of reddish dust and rock. The distinctive red planet, with its polar ice caps and ancient river valleys, would maintain its general structure longer than its inner solar system neighbors. The famous features visible through telescopes, like Olympus Mons, the largest volcano in the solar system, and Valles Marineris, a canyon system that would stretch from New York to California if on Earth, would remain identifiable longer as the planet slowly fragmented. The various rovers and landers sent to explore Mars would continue their missions briefly, transmitting data about the planet's disintegration until communication ceased due to power loss or physical damage. The gas giants, Jupiter, Saturn, Uranus, and Neptune, undergo the most spectacular transformations. These enormous worlds are composed primarily of hydrogen and helium, held in a liquid or even metallic state by the tremendous pressure of their own gravity. When that gravity vanishes, the compression that maintains their structure disappears as well. These outer giants represent a completely different class of planet from the rocky inner worlds. Composed primarily of elements that would normally be gases at the temperatures and pressures found on Earth, they maintain their structure only through the enormous gravitational compression generated by their mass. Jupiter alone contains more than twice the mass of all other planets combined, creating internal pressures millions of times greater than Earth's atmosphere at sea level. Jupiter, the largest planet in our solar system, essentially explodes. Its outer layers of hydrogen and helium, no longer compressed to a liquid state, rapidly expand outward as gas. The pressure within Jupiter is so immense, several million times Earth's atmospheric pressure, that this expansion would be violent and swift. The beautiful bands and storms visible on Jupiter's surface, including the Great Red Spot, dissolve as the atmosphere that creates them disperses into space. This expansion would create a briefly spectacular sight. The familiar striped disk of Jupiter would swell rapidly, its distinct bands becoming less defined as the atmospheric gases dispersed. The Great Red Spot, a storm system that has persisted for at least 400 years and is large enough to contain 2 or 3 Earths, would dissolve as the atmospheric circulation that maintains it ceased. Jupiter's rapid rotation, completing a full turn in just under 10 hours, would add to the complexity of its expansion, with material near the equator being flung outward more rapidly than material near the poles. Deep within Jupiter, something even more dramatic occurs. Under normal conditions, the enormous pressure near the planet's center creates a core of metallic hydrogen. hydrogen compressed so intensely that it behaves like a metal, conducting electricity and generating Jupiter's powerful magnetic field. When gravity disappears, this metallic hydrogen instantly reverts to its gaseous state, releasing an enormous amount of energy in the process. The result is essentially a massive explosion from within, accelerating the planet's disintegration. This phase transition represents one of the most energetic events in our scenario. Hydrogen, normally a gas, becomes metallic under the extreme pressure found in Jupiter's interior, with electrons flowing freely, as in a conductive metal. When this pressure vanishes, the metallic hydrogen reverts explosively to its gaseous state, releasing energy comparable to millions of hydrogen bombs detonating simultaneously. This energy, normally contained by Jupiter's gravitational field, would now drive the planet's expansion even more violently, turning what might have been a relatively gradual dispersal into a catastrophic explosion. Saturn experiences a similar fate, with the added spectacle of its rings breaking apart. These rings, composed of countless ice particles held in orbit around Saturn by gravity, simply scatter in all directions like dust in a sudden breeze. The delicate structures of gaps and divisions, shepherded by small moons, dissolve into disorder. Saturn's many moons, including the intriguing Titan with its thick atmosphere and hydrocarbon lakes, fly off on their own trajectories while beginning their own processes of disintegration. Saturn's iconic rings, spanning nearly 200,000 miles from edge to edge, yet averaging only about 30 feet thick, represent one of the most delicate structures in the solar system. Composed of countless particles of water ice ranging from microscopic dust to chunks the size of houses, these rings are held in their precise orbits by a balance of gravitational forces from Saturn and its many moons. When gravity disappears, this exquisite arrangement shatters instantly. The particles, previously orbiting at different speeds depending on their distance from Saturn, continue on straight-line paths in all directions. The rings do not so much fall apart as explode outward, transforming from a flat, organized disk to an expanding sphere of ice particles. Uranus and Neptune, the ice giants, consist largely of water, ammonia, and methane ices surrounding small rocky cores. As with the gas giants, the loss of gravitational compression causes these worlds to expand dramatically as their frozen components sublimate directly from ice to gas. Their atmospheres disperse, their interiors expand, and they too join the general dissolution of the solar system. These distant worlds, rarely visible to the naked eye and only visited once by spacecraft, contain exotic forms of water, ammonia, and methane compressed into states unlike anything found on Earth. Under the extreme pressure found in their interiors, water exists in phases called hot ice, remaining solid despite temperatures that would normally boil it. When gravity disappears, these strange high-pressure phases transform rapidly, absorbing heat in the process and driving further expansion as they transition to gases. The many moons of our solar system face varied fates depending on their compositions. Rocky moons like our own begin to break apart as their internal pressures seek equilibrium. Ice moons, like Jupiter's Europa or Saturn's Enceladus, both thought to contain subsurface oceans, rupture more dramatically as their liquid interiors are suddenly released from confinement. These hidden oceans, kept liquid by tidal heating and insulated by ice shells, explode outward in spectacular fashion, creating expanding clouds of water vapor and ice crystals around the fragmenting cores. Jupiter's moon Europa provides perhaps the most dramatic example of this process. Beneath its smooth ice shell, scientists believe Europa harbors a subsurface ocean containing more water than all of Earth's oceans combined. This water remains liquid due to tidal heating caused by Jupiter's gravitational influence, despite surface temperatures of about -220 degrees Fahrenheit. When gravity vanishes, the ice shell, no longer compressed by its own weight or held in place by Europa's gravity, begins to crack. The pressurized ocean beneath, suddenly released from confinement, bursts through these cracks in spectacular geysers that rapidly transform into expanding clouds of ice crystals as the water flash freezes in the vacuum of space. Even more distant objects feel the effects. Pluto and the other dwarf planets of the Kuiper Belt continue on straight-line paths away from their former orbits while slowly breaking apart. The countless comets of the Oort cloud, that vast sphere of icy bodies surrounding our solar system, drift outward into interstellar space, maintaining their physical integrity longer than the planets due to their small size and already frozen state. These distant, icy worlds represent the most primitive material in our solar system, largely unchanged since the solar system's formation. Pluto, with its surprisingly complex surface featuring a heart-shaped plain of nitrogen ice and mountains of water ice, would break apart more slowly than the larger planets. The Oort cloud, a theoretical sphere of icy bodies extending perhaps a light year from the Sun, marks the boundary of our Sun's gravitational influence. These trillions of small, icy objects, already barely bound to the solar system, would simply continue on their existing trajectories, now straight lines, rather than the enormous elliptical orbits they once followed. The asteroid belt between Mars and Jupiter, home to millions of rocky bodies, including the dwarf planet Ceres, dissolves as each asteroid continues on its own path. Some head inward toward the region, once occupied by the inner planets. Others move outward. Without gravity to cause collisions and gravitational focusing, the asteroids simply disperse, adding their mass to the general debris now filling the former solar system. This region, once structured by the competing gravitational influences of Jupiter and the Sun, contained enough material to form another planet, had Jupiter's influence not prevented it. Now, these rocky bodies, ranging from dust particles to objects hundreds of miles across, would disperse along countless individual trajectories. Ceres, the largest object in the asteroid belt at nearly 600 miles across, would begin the same process of fragmentation as the larger planets, though more slowly due to its smaller size and solid composition. At the center of this chaos, the Sun itself undergoes the most profound transformation. Like the planets, the Sun is held together by gravity. Its enormous mass creates the tremendous pressure and temperature at its core necessary for nuclear fusion, the process that powers our star and all stars throughout the universe. Without gravity, this delicate balance collapses. The Sun represents the most extreme example of gravitational compression in our solar system. At its core, temperatures reach 15 million degrees Celsius, and pressure exceeds 200 billion times Earth's atmospheric pressure. These conditions force hydrogen nuclei close enough together to overcome their mutual electromagnetic repulsion, allowing the strong nuclear force to bind them together in fusion reactions that convert hydrogen into helium, releasing enormous energy in the process. Every second, the Sun converts more than 4 million tons of matter into energy, producing the heat and light that sustain life on Earth. The Sun's core, compressed to a temperature of 15 million degrees Celsius and a density more than 100 times that of water, suddenly finds itself released from gravitational confinement. The plasma, a soup of electrons and atomic nuclei that makes up the Sun, begins to expand outward in all directions. Nuclear fusion, which requires the extreme density and temperature maintained by gravitational compression, rapidly ceases. The Sun's energy factory shuts down. This cessation of fusion would happen almost instantaneously. The pressure at the Sun's core, created by the weight of all overlying layers, maintains the extreme density needed for fusion. When this pressure disappears, the plasma expands rapidly, with density dropping below the threshold needed for fusion reactions. The production of new energy stops immediately, though the Sun continues to glow from existing heat. But this does not mean the Sun goes dark immediately. The existing heat and light, generated by previous fusion reactions, takes time to travel from the Sun's core to its surface. Under normal conditions, a photon of light generated at the Sun's center can take thousands of years to reach the surface, bouncing between atoms countless times along the way. This stored energy continues to radiate outward even as the Sun expands. The journey of energy from the Sun's core to its surface involves a fascinating process called radiative diffusion. The gamma rays produced by fusion reactions collide with surrounding plasma, gradually losing energy and transforming into lower energy forms of light. By the time this energy reaches the Sun's surface, it has typically been reduced to visible light and infrared radiation. This energy, already created and working its way outward when gravity disappeared, would continue to emerge from the expanding solar material for some time, creating a gradually dimming glow. The expansion of the Sun is not a gentle process. Without the inward pull of gravity to maintain hydrostatic equilibrium, the outward pressure of the hot plasma drives an explosion of unprecedented scale. The Sun essentially becomes a slow-motion supernova, though driven by very different physics than a true stellar explosion. Unlike a true supernova, which is driven by either the collapse of a massive star's core or the runaway fusion reactions of a white dwarf, the Sun's expansion would result from the simple release of pressure. The 400 septillion-ton mass of superhot plasma would expand outward in all directions, initially maintaining much of its heat, but gradually cooling as it spread into an ever larger volume. As the Sun expands, its surface temperature begins to drop. The familiar yellow-white disk we see in our sky would grow larger but cooler, shifting toward the red end of the spectrum. For a brief period, it might resemble a red giant star, the fate our Sun would naturally face billions of years in the future as its hydrogen fuel is exhausted. But this process, which would normally take millions of years, now unfolds over mere days or weeks. The color shift would occur because, as the Sun's photosphere, its visible surface, expanded, the plasma would cool. According to Wien's displacement law, cooler objects emit light with longer wavelengths. The Sun's light would shift from its current yellowish-white, with a temperature of about 5,800 Kelvin, toward orange and then red as the temperature dropped. An observer from a safe distance would see the Sun swell dramatically while its brightness per unit area decreased. The total luminosity would initially remain similar, as the increased surface area would compensate for the reduced brightness, but eventually, both size and luminosity would begin to decrease as the expansion continued and the plasma cooled. Eventually, the expansion dilutes the Sun's material to the point where it no longer emits significant light or heat. The nuclear furnace extinguished, the plasma cooling as it expands, our star fades away. The particles that once comprised it, primarily hydrogen and helium, with traces of heavier elements, disperse throughout the region once occupied by the inner solar system. The Sun does not die so much as it dissolves, its substance returning to the interstellar medium from which it formed 4.5 billion years ago. This process represents a fundamental reversal of stellar evolution. Stars form when gravity overcomes the outward pressure of gas in a molecular cloud, causing material to collapse inward until density and temperature are high enough to ignite fusion. Now, with gravity gone, the Sun returns to a state similar to the nebula from which it formed, though spread over a vastly larger volume and with a slightly different composition due to the nuclear fusion that has occurred during its lifetime. This dispersal of the Sun has profound implications for the temperature of what was once our solar system. The inner planets, those closest to the Sun, initially experience a brief warming as the expanding Sun engulfs them. But this is quickly followed by rapid cooling as the Sun's material thins out and its nuclear reactions cease. Without the steady influx of solar radiation, temperatures throughout the former solar system plummet toward the background temperature of space, close to absolute zero or negative 273 degrees Celsius. The temperature gradient would be dramatic. As the Sun's expanding material passed the orbits of the inner planets, those regions would briefly experience temperatures of thousands of degrees. But this heat pulse would pass quickly as the solar material continued to expand and cool. Behind this wave of heat would come an eternal cold, as the background temperature of empty space, maintained only by the faint glow of distant stars and the cosmic microwave background radiation, took hold permanently. What about the light already emitted by the Sun? The photons traveling outward at the speed of light continue their journey, unaffected by gravity's disappearance. They carry on through space, illuminating what remains of the planets for the last time before heading outward toward the stars. From a distant vantage point, our Sun would appear to shine normally for the approximately 8 minutes it takes light to travel from the Sun to Earth, before beginning to change as the newly emitted light shows the effects of the Sun's expansion. This delay, caused by the finite speed of light, means that observers at different distances would witness the Sun's transformation at different times. An observer on Mercury would see changes after just over 3 minutes, while someone on Neptune would continue to see the normal Sun for over 4 hours after gravity's disappearance. These final photons, emitted before the Sun began to change but still traveling outward, would carry the last image of our solar system as it once was, a kind of fossil light, preserving a moment that had already passed. Over the course of several hours, An observer from a hypothetical space platform far from the solar system would witness the sun grow dimmer and redder before finally fading from view entirely. The planets would cease to be visible by reflected light, though their expanding debris clouds might be detectable by other means. The visual spectacle would be unlike anything ever witnessed by human eyes. Through a powerful telescope, our observer might first see the planets deviate from their predicted positions. Then the sun would begin to expand visibly, its well-defined disk becoming larger but less bright and shifting toward the red end of the spectrum. The planets, normally visible only as tiny points of light, would briefly become small expanding clouds as they disintegrated. Finally, the entire region would fade from view as the once concentrated matter of our solar system dispersed beyond the threshold of visibility. The intricate gravitational dance that once characterized our solar system, with planets tracing elegant ellipses around the sun, gives way to linear diaspora. Each object continues on its own straight-line path, the directions as varied as the points in their orbits where they were located when gravity failed. Some paths lead inward toward where the sun once sat at the system's center, others lead outward toward interstellar space. Over time, the entire solar system expands outward in all directions, like an explosion in extreme slow motion. This transformation from cyclic to linear motion represents perhaps the most fundamental change in our scenario. The solar system as we know it exists because gravity creates closed orbits, paths that return to their starting points, allowing stable, repeating relationships between celestial bodies. Without gravity, only straight-line motion is possible. The elegant ellipses calculated by Kepler and explained by Newton give way to the simpler but less structured paths described by the first law of motion. The cosmic loops that have held our neighborhood together for billions of years unravel into straight lines leading ever outward. This expansion is not uniform. The varying speeds of the different bodies in our solar system create an irregular dispersal pattern. Mercury, zipping along at 30 miles per second, races ahead of Mars at 15 miles per second. The asteroids, each following its own unique trajectory, scatter like wind-blown seeds. The comets of the distant Oort cloud, barely bound to the sun to begin with, drift away at leisurely paces measured in fractions of a mile per second. The pattern of this dispersal would be determined by the positions of all objects at the moment gravity disappeared. Bodies that happened to be moving in similar directions would form loose streams flowing outward together, while those moving in opposite directions would rapidly separate. No two particles would follow exactly the same path, and over time, even objects that started close together would drift apart as tiny initial differences in velocity were magnified by increasing distance. There is a poignant symmetry to this dissolution. The solar system formed from a rotating cloud of gas and dust that collapsed under its own gravity around 4.5 billion years ago. Material drawn toward the center formed the sun, while the remaining dust spinning in a disk around the newborn star gradually coalesced into the planets. Now, with the vanishing of gravity, this process of creation runs in reverse, returning the sun and planets to a dispersed state reminiscent of the nebula from which they formed. The parallel is not exact. The original solar nebula was much more compact than the volume over which our solar system's matter will eventually spread. It also had a clear rotational pattern, which helped shape the disk from which the planets formed. The dispersing material of our gravity-free solar system expands in all directions, with no preference for the plane in which the planets once orbited. And perhaps most significantly, the nebula that formed our solar system was held together by gravity, allowing it to collapse inward and achieve the density needed for star formation. Our dispersing solar matter, expanding forever without gravity's constraining influence, can never coalesce again. But there is a crucial difference. The original solar nebula collapsed because gravity pulled its material inward. Without gravity, there is no force that could ever gather these scattered particles back together again. The dissolution is permanent. The solar system, after its long and eventful life, reaches an irreversible end. The expansion, once begun, would continue forever. In our universe with gravity, the expansion of the cosmos is countered by the mutual gravitational attraction of all matter, potentially leading to a big crunch if the density is high enough. But in our gravity-free scenario, no such counterbalance exists. Each particle follows its straight-line path indefinitely, moving ever farther from its neighbors. The density of matter drops continuously, approaching but never quite reaching zero. This is a true heat death, a state of maximum entropy where organized structures can never again form. What about the human artifacts scattered throughout our solar system? The rovers on Mars, the probes orbiting various planets, the Voyager spacecraft heading toward interstellar space, all continue on their trajectories, though those trajectories are now straight lines rather than the curved paths shaped by gravity. The Voyagers, already destined to leave our solar system, simply continue outward, perhaps the longest-lived remnants of human civilization as they coast through the void for billions of years. Their electronics long dead, but their physical structures largely intact in the emptiness of space. These machines, our robot emissaries to the planets and stars, would ironically become humanity's most enduring legacy. The Voyager spacecraft, launched in 1977 and already in interstellar space when gravity disappeared, carry golden records containing sounds and images from Earth. These records, designed to last for billions of years, might eventually be the only evidence that humanity ever existed, drifting between the stars long after Earth itself has dispersed into cosmic dust. Our solar system is not unique in facing this fate. Throughout the universe, every star system undergoes a similar unraveling. The entire cosmic web of gravitational relationships that has structured the universe since its earliest moments comes undone. Stars fly away from the centers of their galaxies. Galaxies themselves begin to disperse. Galaxy clusters break apart. All the while, the objects themselves, held together by the same now absent force, disintegrate into their component parts. From the smallest planetary systems to the largest galaxy superclusters, gravity provides the binding force that creates cosmic structure. Without it, the universe becomes a homogeneous soup, with matter and energy distributed ever more evenly as time passes. The beautiful spiral galaxies, the dramatic stellar nurseries, the dense globular clusters, all these structured arrangements of matter depend entirely on gravity for their existence. The timescales of this universal dissolution vary enormously. Small objects like asteroids might take years or decades to fully break apart. Planets disintegrate over months to years. Stars explode or disperse over days to weeks, depending on their size and composition. Galaxies might take millions of years to fully disperse, given the vast distances and relatively slow orbital speeds involved. But the end result is the same at every scale: the ordered structures of the cosmos, giving way to an ever-expanding cloud of gas, dust, and radiation. The progression from small to large follows naturally from the physical principles involved. Smaller objects have less internal pressure driving them apart when gravity disappears. They also have shorter internal distances, allowing pressure waves to traverse them more quickly. Larger objects contain more stored potential energy in their compressed interiors, driving more violent expansions. Thus, the pebble takes longer to crumble than the planet longer than the star sooner than the galaxy. In our solar system, after a century has passed, little recognizable structure remains. The sun is gone, replaced by a vast and thinning cloud of hydrogen and helium mixed with traces of heavier elements. The planets exist only as dispersing fields of debris, their distinctive characteristics increasingly blurred as they mix with the general medium of space. The comets and asteroids, more numerous but individually smaller, have scattered far and wide, some escaping into interstellar space, others drifting through the expanding debris field that was once their home system. The material does not disappear, it simply spreads out. Conservation of matter and energy, one of the most fundamental principles of physics, ensures that every atom, every electron, every photon that made up our solar system continues to exist. But the relationships between these components, the structures they once formed, the ordering principles that gave them meaning, all these are lost as entropy increases toward its maximum possible value. After 1,000 years, even an advanced civilization with powerful telescopes would be hard-pressed to determine that a planetary system had once existed here. After 1,000,000 years, the region occupied by our former solar system would be indistinguishable from the surrounding interstellar medium, save perhaps for a slightly higher concentration of elements heavier than hydrogen and helium, the chemical legacy of the nuclear fusion that once powered our sun. all evidence that an orderly solar system once occupied this region of space would be erased. The slight enrichment in heavier elements might suggest to a hypothetical future xenoarchaeologist that a star once burned here, but it would be difficult or impossible to determine how many planets it hosted, what their compositions were, or whether they harbored life. The story of our corner of the cosmos, built up over billions of years of gravitational interaction, would be rendered illegible. In a universe still governed by gravity in regions beyond our solar system, this dispersed material might eventually be drawn into new star systems, forming new planets, perhaps even nurturing new life. The atoms that once made up our world could find themselves incorporated into countless new structures across the galaxy. But in our scenario, where gravity has simply ceased to exist throughout the cosmos, no such cosmic recycling can occur. The disintegration marks not just the end of our solar system, but the beginning of the end for all ordered structures in the universe. Without gravity's ordering influence, new stars cannot form, planets cannot coalesce from the debris of previous systems, galaxies cannot assemble from dispersing stars. The generative cycle that has characterized our universe since the Big Bang comes to a permanent halt. The cosmos enters a terminal phase, coasting on its accumulated structures until they all dissolve into their constituent parts, never to be reassembled. And so, our journey outward from Earth shows us that the unraveling caused by gravity's disappearance knows no bounds. From the smallest moon to the mightiest star, from a grain of dust to an entire planet, all matter that was once gathered and shaped by gravity now returns to a state of expanding disorder. The solar system, our cosmic neighborhood for the entirety of human existence, dissolves into memory, its substance scattered across the void, its intricate architecture lost to the linear paths of a gravitationless cosmos. As we expand our view beyond our dissolving solar system, we witness the universe at large coming undone. The effect of gravity's disappearance cascades outward, touching everything from nearby star systems to the most distant galaxies visible to our telescopes. The cosmic architecture, built over 13.8 billion years through gravity's patient work, begins its inexorable decline. Our Milky Way galaxy, a vast spiral of stars, gas, and dust spanning 100,000 light-years, holds roughly 400 billion stars, each with its own planetary systems, nebulae, and other cosmic structures. All of it begins to disintegrate simultaneously when gravity vanishes. The effect, if we could somehow observe it from above the galactic plane, would be both beautiful and terrifying. The elegant spiral arms of our galaxy, maintained by density waves propagating through its structure, begin to straighten out as stars no longer feel the gravitational influence of their neighbors or the galactic center. Stars continue moving at their current velocities, now in straight lines rather than curved orbital paths. Some head outward, away from the galactic center. Others, depending on where they were in their orbits when gravity failed, head inward or tangentially. At the center of our Milky Way sits a supermassive black hole, Sagittarius A star, with a mass of about 4 million times that of our Sun. Black holes represent gravity in its most extreme form, where space-time is curved so severely that not even light can escape beyond the event horizon. When gravity disappears, black holes undergo perhaps the most dramatic transformation of all cosmic objects. The event horizon, that boundary from beyond which nothing can return, simply vanishes. The singularity at the center, where matter was compressed to infinite density and space-time was infinitely curved, no longer has the gravitational force needed to maintain its state. The immense amount of matter and energy contained within the black hole explodes outward in all directions. This is not a conventional explosion like a supernova, but something far more exotic, as space-time itself rebounds from its previously curved state. The physics of what happens at this moment strains our understanding and our ability to describe it. The matter and energy that emerges may no longer resemble anything we would recognize. Information that was thought to be lost forever beyond the event horizon potentially becomes accessible again, though in what form is difficult to say. The release of energy would be enormous, briefly outshining the combined light of all stars in the galaxy. Similar events unfold at the locations of stellar mass black holes scattered throughout the galaxy, the remnants of massive stars that ended their lives in supernova explosions. These smaller but still immensely powerful objects also release their captive matter and energy, adding to the general chaos spreading throughout the Milky Way. Neutron stars, another type of stellar remnant where gravity has compressed matter to incredible densities, also undergo catastrophic changes. These objects, with masses comparable to our Sun, but compressed into spheres just 12 miles in diameter, have densities so extreme that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. When the gravitational force holding this ultra-dense matter in place disappears, neutron stars essentially explode. The neutrons, no longer compressed beyond normal atomic densities, begin to decay into protons and electrons, eventually forming hydrogen. The energy released in this process is tremendous, creating brilliant flashes across the galaxy. White dwarfs, the remnants of sun-like stars that have exhausted their nuclear fuel, face a similar but less violent fate. These objects are supported against further collapse by electron degeneracy pressure, not by ongoing fusion reactions. Without gravity counterbalancing this pressure, white dwarfs expand rapidly, transforming from star-sized diamonds back into diffuse clouds of primarily carbon and oxygen. Throughout the Milky Way, stars of all types undergo the same process we described for our Sun. The massive, hot, blue stars, which live fast and die young, explode most dramatically as their intense internal pressures are suddenly released. The smaller, cooler red dwarfs, the most common type of star in our galaxy, expand more gently, but still ultimately disperse. The interstellar medium, the gas and dust that fills the space between stars, begins to disperse as well. Under normal conditions, this material clumps together under its own gravity to form new stars in a continuous cycle of stellar birth and death. Without gravity, not only does this star formation cease, but the existing clouds begin to expand outward in all directions. The beautiful nebulae, both the remnants of dead stars and the birthplaces of new ones, lose their structure and dissolve into the void. The thousands of star clusters in our galaxy, both the ancient globular clusters orbiting in the galactic halo and the younger open clusters in the spiral arms, break apart as their stars scatter in all directions. These stellar groupings, some containing millions of stars in a relatively compact volume, had been held together by their mutual gravitational attraction for billions of years. Now, they dissolve like sugar crystals in water, their component stars joining the general diaspora. Our nearest galactic neighbors, the Large and Small Magellanic Clouds, visible from the southern hemisphere as faint smudges of light, undergo the same dissolution as the Milky Way itself. These satellite galaxies, orbiting our own like moons around a planet, not only disperse internally, but also continue on straight-line paths away from their former orbits around the Milky Way. The Andromeda Galaxy, the nearest major galaxy to our own, at a distance of 2.5 million light-years, faces the same fate. Under normal circumstances, Andromeda and the Milky Way are being drawn together by their mutual gravitational attraction, destined to collide and merge about 4.5 billion years in the future. With gravity gone, this cosmic dance is called off. Instead, both galaxies dissolve from within while maintaining their current relative positions, neither approaching nor receding from each other due to gravitational effects, though the general expansion of the universe continues to carry them apart. This pattern repeats throughout the cosmos. Every galaxy, from giant ellipticals to tiny irregulars, comes apart as the stars within them scatter. Galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity, dissolve as their member galaxies fly off in all directions. The great voids between galaxy clusters grow ever larger as the universe loses its lumpy, clustered structure. The cosmic web, that vast network of galaxy filaments and superclusters that forms the large-scale structure of the universe, begins to homogenize. This web, revealed by careful mapping of galaxy positions, shows that matter in the universe is not evenly distributed, but concentrated along interconnected filaments with vast voids between them, rather like a sponge or Swiss cheese. This structure formed in the early universe as tiny fluctuations in the density of matter were amplified by gravity, drawing more and more material into the denser regions. Without gravity, this pattern begins to wash out as galaxies and gas clouds drift away from the filaments, gradually filling in the voids. It would take an immense amount of time for this homogenization to complete, however. The distances between galaxies are so vast that even moving at hundreds of kilometers per second, they would take billions of years to spread evenly throughout space. But the process is inevitable. Without gravity, the universe has lost its architect, the force that created structure from uniformity. The timescale of this galactic dissolution varies enormously depending on the objects involved. Individual stars explode or disperse within days or weeks. Star clusters might take thousands of years to fully scatter. Galaxies would require millions or even billions of years to completely lose their structure, though the process begins immediately when gravity disappears. What about the planets orbiting other stars? We now know that most stars host planetary systems, though these tend to be quite different from our own. Some have massive gas giants orbiting incredibly close to their stars, completing an orbit in just days. Others have multiple Earth-sized worlds packed into orbits tighter than that of Mercury around our Sun. Still others have planets in much more distant orbits. All of these worlds, from fiery super-Earths to frigid gas giants, face the same fate as the planets in our solar system. They fly off on tangential paths, while simultaneously breaking apart from within as their internal pressures are released. If life exists elsewhere in the universe, which seems increasingly likely given the abundance of potentially habitable worlds, it too would face extinction in this gravitationless scenario. Some forms of life might survive longer than others. Underground microorganisms on worlds with thick crusts might briefly outlast surface dwellers. Advanced civilizations with space technology might recognize what was happening and attempt to create artificial habitats, but these would be temporary measures at best. Without the organizing force of gravity, complex structures of all kinds, including biological ones, cannot persist indefinitely. Dark matter, that mysterious substance that appears to make up about 85% of the matter in the universe based on its gravitational effects, poses an interesting question in our scenario. We don't know exactly what dark matter is, though there are many theories ranging from undiscovered particles to modifications of gravity itself. If dark matter particles interact through gravity but not through other forces, they would cease to affect ordinary matter when gravity disappears. Their effects on galaxy rotation and gravitational lensing would instantly vanish. If, on the other hand, dark matter represents a modification of how gravity works, then its effects would disappear along with gravity itself. Dark energy presents another intriguing aspect of our thought experiment. This even more mysterious component, which appears to be driving the accelerating expansion of the universe, might be a property of space itself rather than a conventional force or type of matter. If gravity ceased to exist, would dark energy continue to expand the universe? The answer lies beyond our current understanding, but it seems plausible that whatever process causes space itself to expand would continue, now unopposed by the attractive force of gravity that had been slowing it down. The cosmic microwave background radiation, the afterglow of the Big Bang visible in all directions as a nearly uniform glow of microwave radiation, would remain largely unchanged by the disappearance of gravity. These photons, released about 380,000 years after the Big Bang when the universe cooled enough for atoms to form, have been traveling through space ever since. They would continue their journey through the increasingly homogeneous cosmos, their wavelength still being stretched by the expansion of space. As time passes in our gravity-free universe, the differences between various types of celestial objects begin to blur. Stars, having expelled their outer layers and ceased fusion, cool to become diffuse clouds of predominantly hydrogen and helium. Planets break apart into scattered fields of dust and gas. Black holes evaporate in brilliant bursts of exotic radiation. Everything trends toward an increasingly uniform state, with matter and energy spread ever more thinly across an ever-expanding space. The ultimate fate of such a universe is both bleak and strange. Without gravity to create new stars from interstellar gas, the existing stars eventually burn out or break apart. No new stars can form. Similarly, without gravity to overcome the repulsive force between atomic nuclei, nuclear fusion ceases throughout the cosmos. The universe grows cold and dark, not on the timescale of trillions of years as current models predict, but much more rapidly, perhaps within billions of years of gravity's disappearance. The matter that once made up stars, planets, galaxies, and living beings drifts ever outward, becoming increasingly diffuse. Atoms remain intact, held together by the electromagnetic force. Molecules can still form through chemical bonding, but larger structures become impossible to maintain without gravity. The universe approaches a state of near-perfect entropy, with energy and matter distributed almost uniformly throughout space. Such a universe would be barely recognizable compared to the one we inhabit. The night sky, once filled with the light of countless stars gathered into the band of the Milky Way, would grow darker with each passing year as stars dispersed and failed. Eventually, no stars would be visible at all from any vantage point. The cosmos would become an ever-expanding void, sparsely populated by atoms and molecules, with the occasional chunk of rock or ice as the only reminder that more complex structures once existed. Is such a universe truly dead? Not entirely. Atoms would continue to exist, occasionally colliding and forming simple molecules. Radiation would continue to travel through space. The fundamental particles, electrons, protons, neutrons, and others, would persist. But without gravity, the universe would have lost its capacity for complexity. No new stars, planets, or galaxies could form, and without these, no new life could arise. There is something deeply poignant about this thought experiment, this imagining of a universe without its most fundamental organizing force. For all its weakness relative to the other fundamental forces, gravity creates the conditions necessary for complexity to evolve. It gathers diffuse matter into stars, where nuclear fusion creates the heavy elements necessary for planets and life. It shapes those planets, giving them atmospheres and climates suitable for biology. It regulates the internal processes of those worlds, from weather patterns to geological activity. In short, gravity creates the stage upon which the drama of existence unfolds. To witness the disappearance of gravity is to understand, by its absence, just how crucial this force is to everything we know. As we watch the galaxies unravel and the cosmos dissolve into uniformity, we gain a profound appreciation for the delicate balance that allows our universe to exist as it does, with its rich tapestry of structure and complexity at every scale, from atoms to superclusters. And so, as we contemplate the galactic fallout from gravity's disappearance, we are reminded that what we are really observing is the end of possibility itself, at least for any form of existence resembling our own. Without gravity, the universe loses not just its structures but its potential, its capacity for the new and the complex, its ability to create the conditions where consciousness can emerge to wonder at the stars. Our exploration of a universe without gravity now leads us to perhaps the most profound consequences of all. Beyond the physical disintegration of planets, stars, and galaxies lies an even deeper transformation. The very fabric of reality, space-time itself, undergoes radical change when gravity vanishes. To understand this, we must delve into one of the most revolutionary insights of modern physics, Einstein's general theory of relativity. According to Einstein, gravity is not a force in the conventional sense. Rather, it is a manifestation of the curvature of space-time. Massive objects like stars and planets create depressions in this four-dimensional fabric, rather like heavy balls placed on a trampoline. Other objects, from planets to photons of light, follow the curves created by this warping. What we experience as gravity is actually the effect of moving through curved space-time. When we imagine gravity disappearing, we are essentially imagining space-time suddenly becoming flat everywhere. The dimples, wells, and valleys created by masses throughout the universe would instantly smooth out. The geometry of space around every star, planet, galaxy, and cluster would transform from curved to flat. This flattening would have immediate consequences for the passage of time itself. In Einstein's framework, gravity affects not just space, but time as well. Time passes more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. We observe this effect in precise measurements. Clocks at higher altitudes, where Earth's gravity is slightly weaker, run fractionally faster than those at sea level. GPS satellites must account for this difference, or they would quickly become inaccurate. In the extreme case of a black hole, time dilation becomes so pronounced that at the event horizon, time appears to stop completely from the perspective of a distant observer. Inside the black hole, space-time is so severely warped that our conventional understanding of time breaks down entirely. When gravity vanishes, these variations in the flow of time would disappear as well. Time would begin to pass at the same rate everywhere in the universe. something that has never been true since the earliest moments after the Big Bang. The synchronization would be instantaneous from our perspective, though due to the finite speed of light, it would take time for information about distant regions to reach observers elsewhere. One of the most dramatic manifestations of this temporal equalization would occur at the locations of former black holes. As we discussed earlier, black holes would essentially evaporate when gravity disappears. The singularities, those points of infinite density and infinite space-time curvature at their centers, would cease to exist as the matter once confined there expands outward. This has profound implications for information. According to quantum mechanics, information cannot be destroyed, yet black holes seem to erase information about anything that falls into them, creating a paradox that has puzzled physicists for decades. If black holes were to suddenly disappear, what would happen to all the information they had seemingly consumed throughout their existence? The answer might be that this information returns to the wider universe, encoded in the radiation and matter released as the black holes evaporate. But the form it takes might be unrecognizable, scrambled beyond any hope of reconstruction. Stars and planets that fell into black holes billions of years ago would not re-emerge intact. Instead, their fundamental particles and the relationships between them would be released, carrying their information in encrypted form. As space-time flattens throughout the universe, another profound change occurs. In a universe with gravity, space itself can expand or contract. Indeed, our universe has been expanding since the Big Bang, and this expansion is accelerating due to the influence of dark energy. This expansion is not objects moving through space, but space itself stretching, carrying galaxies along with it, like dots on an inflating balloon. Without gravity to counteract this expansion, what happens? If dark energy is a property of space itself, as many physicists believe, it would continue to drive the universe's expansion, now unopposed by gravity's attractive force. The expansion would accelerate even faster than it currently does. Galaxies, already flying apart as they disintegrate internally, would be carried away from each other at an ever-increasing rate by this enhanced cosmic expansion. In such a scenario, the ultimate fate of the universe would be reached much sooner than current models predict. In the standard lambda-cold dark matter model, with gravity still operating, the universe expands forever, but does so gradually enough that galaxies, stars, and even planets can continue to exist for trillions of years. Without gravity, the combination of structural disintegration and accelerated expansion would bring about the heat death of the universe much more rapidly. The heat death is a concept from thermodynamics, describing a state where energy is distributed so uniformly throughout a system that no more work can be extracted from it. Applied to the universe, it refers to a state where all stars have burned out, all black holes have evaporated, and all matter and energy are spread so thinly and uniformly that no significant temperature differences exist anywhere. Without such differences, no processes can occur, no work can be done, and time itself loses its significance. In a very real sense, nothing happens in a universe that has reached heat death. In our standard universe with gravity, this heat death lies in the extremely distant future, perhaps 100 trillion years from now or even later. In our gravitationless scenario, it might occur within billions of years, a mere eye blink in cosmic terms. The relationship between gravity and quantum mechanics presents another fascinating aspect of our thought experiment. These two pillars of modern physics, general relativity describing gravity and quantum mechanics describing the other three fundamental forces, have resisted unification despite decades of effort by the world's leading theoretical physicists. The problem is that general relativity describes space-time as smooth and continuous, while quantum mechanics describes reality as discrete and probabilistic at the smallest scales. In regions of extreme space-time curvature, such as the centers of black holes or the earliest moments of the Big Bang, both theories are needed to describe what happens, yet they give incompatible answers. This suggests that a deeper theory, often called quantum gravity, must exist to reconcile them. If gravity were to suddenly disappear, the need for such a unified theory might vanish as well. With space-time now flat everywhere, general relativity would become trivial, as its key feature, the description of curved space-time, would no longer be relevant. Quantum mechanics would reign supreme, describing all remaining forces and interactions in the universe. The quantum foam, the theorized microscopic fluctuations in the fabric of space-time itself, might become more uniform and less dynamic without gravity to influence it. The vacuum of space itself would be affected. In quantum field theory, even empty space is not truly empty, but filled with virtual particles constantly popping in and out of existence. These vacuum fluctuations are influenced by gravity, particularly in regions of strong space-time curvature. Without gravity, the nature of the vacuum might change in subtle but significant ways, potentially affecting the behavior of quantum fields throughout the universe. One of the most profound questions raised by our thought experiment concerns the arrow of time. Why does time flow in one direction only, from past to future? This asymmetry appears to be connected to the increase of entropy, the measure of disorder in a system, as described by the second law of thermodynamics. Systems naturally evolve from ordered to disordered states, never the reverse, giving time its apparent direction. Gravity plays a crucial role in this process by creating ordered structures from disordered ones. When gas clouds collapse under their own gravity to form stars, the decrease in entropy within the star is more than offset by the increase in entropy from the heat and light it radiates. Gravity essentially creates local pockets of order in a universe trending toward disorder, allowing complex structures like galaxies, stars, planets, and ultimately life to exist temporarily within the larger flow toward entropy. Without gravity, this capacity to create local order disappears. The universe would have no mechanism to counteract, even temporarily, the inexorable increase in entropy. The arrow of time would still point in the same direction, but the journey toward maximum entropy would be more uniform and direct, without the detours through complexity that gravity makes possible. The implications for consciousness are particularly striking. Our ability to perceive time passing, to remember the past and anticipate the future, depends on the arrow of time and the entropy gradient it creates. Our brains store information as ordered patterns, temporarily resisting the trend toward disorder through the energy we derive from food, which ultimately comes from the sun, which exists only because of gravity. Without gravity creating the conditions for this local decrease in entropy, consciousness as we understand it could not exist. Even if some form of organized matter could temporarily persist in a gravitationless universe, it would lack the energy gradients needed to process information and maintain the complex, ordered state that thinking requires. In a very real sense, then, the disappearance of gravity would mean the end not just of physical structures, but of the possibility of mind itself. The universe would not only become uniform in its material composition, but would lose the capacity to know itself through conscious observers. The cosmos would still exist, but with no one to experience it, to measure it, to wonder about it. This speaks to a profound relationship between gravity, complexity, and meaning. By creating the conditions for structure and organization to emerge from uniformity, gravity makes possible the extraordinary sequence that leads from hydrogen clouds to stars, from stars to planets, from planets to life, and from life to consciousness. Each step in this sequence depends crucially on gravity, providing the framework within which other forces can create complexity. When we look up at the night sky and see the stars arranged in familiar constellations, we are seeing the work of gravity made visible across unimaginable distances. When we feel the weight of our bodies against the Earth, we are experiencing the same force that shapes the largest structures in the cosmos. When we trace the history of the atoms in our bodies back to the stars that forged them, we are following a path laid out by gravity over billions of years. In this light, gravity appears not just as a physical force, but as the cosmic principle of relationship itself. It is the force through which everything in the universe maintains connection with everything else. No object, no matter how distant, is completely free from the gravitational influence of all other objects. We are, quite literally, held in the universe by the sum of all matter and energy within it. The disappearance of gravity would thus represent not just a physical catastrophe, but a metaphysical one as well, the severing of the fundamental connections that bind the cosmos into a coherent whole. Without these connections, space itself would lose much of its structure and significance, becoming merely the empty stage on which disconnected particles drift ever further apart. Time too would lose its richness and texture. Without gravitational time dilation, Without the complex interplay of matter and space-time that gives the universe its dynamism, time would become uniform and featureless. The cosmic story would simplify into a brief epilogue, an undifferentiated fade to entropy, without the intricate chapters of structure and complexity that gravity makes possible. And so we see that in a universe without gravity, we lose not just the ground beneath our feet, not just the planets and stars, not just the galaxies and clusters, but the very framework that gives meaning and structure to existence itself. Space becomes flat and increasingly empty. Time becomes uniform and ultimately meaningless. The rich tapestry of cosmic evolution, from hydrogen clouds to conscious minds contemplating their own origins, unravels completely. This thought experiment, impossible though it may be in reality, illuminates by contrast the extraordinary gift that gravity represents. It is the force that creates both the stage and the conditions for the cosmic drama to unfold. It is the unseen hand that has shaped everything we know from the first moments after the Big Bang to the present moment, as you listen to these words. It is, in a very real sense, what holds the universe and us together. After exploring the cosmic dissolution that would follow gravity's disappearance, we turn now to a more intimate question. In this new reality, could life as we know it, or perhaps life as we don't know it, possibly endure? The answer requires us to examine the profound relationship between gravity and biology, a connection far deeper than we might initially imagine. Life on Earth evolved entirely under gravity's constant influence. From the earliest single-celled organisms to the most complex animals and plants, every living thing has adapted to function within Earth's gravitational field. This adaptation is so fundamental that we rarely consider how thoroughly it shapes all biological processes. Consider the simple act of circulation. In taller land animals, the heart must work against gravity to pump blood upward to the brain. Giraffes have evolved extraordinarily high blood pressure and specialized blood vessels to accomplish this feat. Human bodies have developed valves in our leg veins to prevent blood from pooling in our lower extremities. Even the simple act of standing up involves a complex network of reflexes that maintain blood pressure as gravity pulls blood away from the brain. Plants structure themselves entirely around gravity's pull. They grow roots downward toward the center of Earth and stems upward against gravitational force. This directional growth, called gravitropism, is guided by specialized cells containing dense starch grains that settle to the bottom of the cell under gravity's influence, telling the plant which way is down. Without this guidance, plants would grow in random directions, unable to find soil for nutrients or light for photosynthesis. On a larger scale, gravity organizes ecosystems. It creates the pressure gradients that drive water downhill, forming rivers and shaping landscapes. It maintains the density differences that allow lighter freshwater to float atop denser saltwater in estuaries, creating unique habitats. It keeps our atmosphere pressed against the Earth, maintaining the air pressure needed for respiration and weather patterns that distribute water and heat. When gravity vanishes, all these biological processes and ecological systems would be immediately disrupted. Blood would no longer flow preferentially to the lower body, causing a sudden redistribution of fluids within organisms. Animals accustomed to supporting their weight against gravity's pull would find their muscles suddenly overpowered, pushing them off surfaces and leaving them floating helplessly. Plants would lose their sense of up and down, with their gravitropism mechanisms rendered useless. Seeds would no longer sink into soil, roots would fail to grow downward. The organized structure of forests, grasslands, and other terrestrial ecosystems would disintegrate as plants drifted out of the ground. Aquatic creatures might initially fare better than land dwellers. Many fish, especially those with swim bladders, can adjust their buoyancy to hover at different depths. In the absence of gravity, this ability might temporarily allow them to navigate within their water droplets using swimming motions. But as the droplets themselves broke apart and water began to boil away in the vacuum of space, even these advantages would quickly become meaningless. The most immediate threat to most life forms would be the loss of atmosphere. As we've already described, air molecules would begin drifting away from Earth as soon as gravity disappeared. The resulting vacuum would be lethal to almost all multicellular organisms within minutes. Without oxygen, animals would suffocate. Without carbon dioxide, plants would be unable to photosynthesize, even if they somehow remained intact and illuminated. Temperature regulation would become another insurmountable challenge. Without an atmosphere to distribute heat and moderate temperature extremes, any surface facing the sun would rapidly overheat, while surfaces in shadow would quickly freeze. Living tissues cannot withstand such extreme temperature gradients, which would cause cells to rupture as water expanded when freezing or boiled when overheating. Pressure changes would be equally devastating. Organisms adapted to Earth's atmospheric pressure would experience rapid decompression as air dispersed. Gases dissolved in bodily fluids would come out of solution, forming bubbles in blood and tissues, a condition similar to what deep-sea divers know as the bends, but far more severe and widespread. Cell membranes would rupture as the pressure differential between internal and external environments became too great. Reproduction, the most fundamental biological process, would be profoundly disrupted. Many reproductive strategies depend on gravity, from the dispersal of pollen and seeds to the development of embryos. Fertilization often relies on eggs settling to the bottom of water bodies, where sperm can find them. Embryonic development in many species critically depends on gravity's cues to orient the growing organism and trigger proper differentiation of tissues. Even if individual organisms could somehow survive these initial catastrophes, perhaps through extraordinary adaptations or technological interventions, the ecological webs that support most life forms would be irreparably severed. Food chains would collapse as producers, consumers, and decomposers alike succumbed to the harsh new conditions. The intricate relationships between species, built over millions of years of coevolution, would dissolve as quickly as the physical structures of the planet itself. Yet life is remarkably tenacious and diverse. While most organisms would perish almost immediately in our gravitationless scenario, certain extremophiles might briefly persist. These extraordinary microorganisms have evolved to survive conditions that would be lethal to most life forms, offering tantalizing hints about the limits of biological resilience. Tardigrades, microscopic animals colloquially known as water bears, can enter a dehydrated state called anhydrobiosis, in which their metabolism virtually stops. In this condition, they can survive extreme temperatures, radiation, pressure, and even the vacuum of space for limited periods. Experiments on the International Space Station have shown that some tardigrades can survive direct exposure to space for up to 10 days. Certain bacteria are even more resilient. Deinococcus radiodurans can withstand radiation levels 1,000 times greater than would kill a human, allowing it to survive in highly radioactive environments. Bacillus subtilis spores have remained viable after 6 years in space, protected only by their tough outer coating. These examples suggest that while complex, multicellular life would quickly perish without gravity, simpler organisms might briefly survive in protective states. Bacterial spores and dehydrated tardigrades, already present in Earth's upper atmosphere or embedded in debris flung into space, could potentially remain viable for years or even decades as they drifted through the void. However, long-term survival would face additional challenges beyond the immediate crisis. Without gravity, the formation of planets and other celestial bodies where life could gain a foothold would cease. The accretion of cosmic dust and gas into planetesimals, the first step in planet formation, depends entirely on gravitational attraction. No new worlds could arise to replace Earth as a cradle for life. Even if some extraordinarily hardy microorganisms survived the initial catastrophe, drifting through space in a dormant state, they would eventually encounter limits to their endurance. Cosmic radiation would gradually damage their DNA beyond repair. Their protective coatings would degrade from exposure to ultraviolet light and atomic oxygen. The extreme cold of space would cause cumulative stress to cellular structures. Within years, decades, or at most centuries, even these most resilient life forms would likely succumb. What about artificial habitats? Could human technology create environments where life could continue without gravity? Even before gravity's disappearance, we had developed limited life support systems for space exploration. The International Space Station, for example, recycles water, generates oxygen, and maintains atmospheric pressure and temperature within habitable ranges. In principle, more advanced versions of such systems could temporarily sustain human life and selected other organisms. But these systems face fundamental limitations in a universe without gravity. The processes used to recycle air and water often rely on gravity for separation of components. Growing plants for food and oxygen regeneration becomes far more complicated without gravity's guidance for root and stem growth. Even something as basic as keeping water contained and flowing through pipes becomes problematic when it forms floating globules rather than flowing downhill. More importantly, artificial habitats require energy to maintain their internal conditions against the entropy of the universe. On Earth, almost all energy ultimately comes from the sun, whether directly through solar radiation or indirectly through fossil fuels, wind, or hydroelectric power. All of these energy sources would fail in a gravitationless universe. Solar panels might briefly continue generating electricity if they remained oriented toward the expanding and cooling sun, but as stars dispersed and failed without gravitational compression, even this energy source would disappear. Nuclear power, whether through fission or fusion, might provide energy for longer periods, allowing habitats to maintain life support systems for decades or perhaps centuries. But even nuclear reactions would eventually be affected by the changing physics of a gravitationless universe. The pressure and density conditions that enable fusion in stars would no longer exist naturally, and artificial fusion would become increasingly difficult to maintain as the necessary fuels dispersed throughout space. Furthermore, all artificial habitats would face the problem of dissipating waste heat. On Earth or in space with gravity intact, cooling systems can use convection to carry away excess heat. Without gravity, heat transfer becomes much more difficult, limited to radiation and conduction. Any closed system generating energy internally would eventually overheat unless it could effectively radiate that heat into space. The psychological aspects of long-term survival cannot be overlooked either. Humans and other social animals have evolved to live with the sensory and social stimulation provided by Earth's varied environments and diverse life forms. The isolation and confinement of artificial habitats, combined with the knowledge that the universe outside was becoming increasingly hostile to life, would create enormous psychological stress. Maintaining mental health in such conditions would be at least as challenging as maintaining physical health. Given all these constraints, it seems virtually certain that life as we know it could not survive indefinitely in a universe without gravity. The most resilient organisms might persist for years or decades. The most advanced artificial habitats might extend this time frame to centuries or perhaps millennia. But eventually, the inexorable trend toward entropy, unopposed by gravity's organizing influence, would claim even these last outposts of biological complexity. This realization leads us to a profound insight about life and gravity. Life as we understand it is not merely adapted to gravity, it is an expression of the same underlying principle. Both gravity and life work against the universe's tendency toward uniform disorder. Gravity creates distinct structures, concentrations of matter and energy that enable the chemical and physical processes life requires. Life maintains and increases its internal order by harnessing energy gradients, which exist primarily because gravity has created non-uniform distributions of matter and energy throughout the cosmos. In this sense, the disappearance of gravity would not simply make survival difficult for existing life forms, it would eliminate the conditions that make life possible in a more fundamental way. Without gravity's ability to create local decreases in entropy, the physical foundation for biological complexity would cease to exist. The universe would still contain all the elements necessary for life, but scattered so widely and uniformly that they could never again assemble into the intricate structures required for even the simplest living systems. As we contemplate the relationship between gravity and life, we recognize that our existence is woven into the fabric of the universe in ways we rarely acknowledge. The same force that keeps our feet on the ground is also responsible for creating the stars that forged the elements in our bodies, the planet that became our home, and the conditions that allowed life to emerge and evolve into forms capable of understanding their own origins. Without gravity, the universe would not only lose its structure but its potential for the kind of complexity that makes consciousness possible. In such a cosmos, there would be no one to witness the stars, no one to wonder about their origins, no one to imagine what might have been in a universe where matter could still come together to explore its own nature. And so we conclude that in a universe without gravity, life is ultimately impossible. Not just our kind of life, but any kind of life that requires structured complexity maintained against the tide of entropy. The disappearance of gravity would mean the disappearance of life's foundation, an end not just to living things, but to the possibility of living things, now and forever after. Having explored the catastrophic consequences of gravity's disappearance, a question naturally arises: could gravity be artificially recreated? If the fundamental force that shapes our universe were to vanish, could intelligent beings find ways to simulate its effects, or perhaps even generate a replacement? This question leads us from hard science into more speculative realms, yet remains grounded in physical principles we understand today. The most familiar form of artificial gravity comes from rotation. We see this concept frequently in science fiction, from the vast rotating space stations in works like 2001, A Space Odyssey, to the spinning habitats of more recent imaginings. The physics behind this approach is straightforward and based on principles we already understand. When an object rotates, it creates centripetal force, pulling everything inside toward the outer rim. This force feels remarkably similar to gravity from the perspective of someone inside the rotating structure. Stand inside a large enough rotating cylinder, and your feet would be pulled toward the curved floor just as they are pulled toward Earth's surface under normal gravity. This approach has practical limitations, however. The force created depends on both the radius of rotation and the speed of rotation. A small rotating habitat would need to spin very quickly to simulate Earth's gravity, which would create problematic side effects. The Coriolis effect, which causes moving objects to appear to deflect from a straight path when viewed from a rotating reference frame, becomes noticeable and disorienting at high rotation rates. Humans experience dizziness, nausea, and difficulty moving normally when this effect is pronounced. To minimize these problems, a rotating habitat would ideally have a large radius, allowing it to spin more slowly while still generating the desired force. A space station designed to provide one Earth gravity through rotation might need to be hundreds of meters in diameter to keep rotation rates comfortable for human occupants. Even before gravity disappeared, engineers and scientists had seriously considered such designs for space habitats. One of the most famous concepts, the O'Neill cylinder, proposed by physicist Gerard O'Neill in the 1970s, envisioned massive rotating habitats several kilometers long and kilometers in diameter, capable of housing thousands of people with an Earth-like environment inside. However, these rotating habitats face a fundamental limitation in our scenario. They don't actually create gravity. They merely simulate its effects through centripetal force. In a universe where true gravity has vanished, these structures could provide localized environments where people and other organisms might move in ways similar to how they did under gravity's influence. But they would do nothing to address the larger cosmic consequences of gravity's disappearance, from the breakdown of stars and planets to the disintegration of galaxies and the flattening of space-time. Could more advanced technologies do better? Theoretical physics suggests several speculative approaches to generating actual gravitational forces, though all remain firmly in the realm of science fiction with our current technological capabilities. One approach stems from Einstein's general relativity, which tells us that energy and mass are equivalent and both curve space-time to create gravity. If an extremely advanced civilization could somehow concentrate enough energy in a small space, they might theoretically create a gravitational field. The practical challenges would be immense, however. The energy requirements would be astronomical, likely requiring something akin to the entire output of a star to create even a modest gravitational field. Another speculative approach involves manipulating the hypothetical particle associated with gravity, the graviton. While gravitons remain theoretical and have never been directly observed, most quantum theories of gravity predict their existence. If gravitons could somehow be generated and controlled, perhaps a gravitational field could be artificially produced, similar to how we can generate electromagnetic fields by moving charged particles. The technical challenges here are even more daunting. Gravitons, if they exist, interact with matter far more weakly than electromagnetic forces, making them extraordinarily difficult to manipulate. The energy and technology required would likely be far beyond anything we can currently imagine. Some more exotic theoretical frameworks suggest additional dimensions beyond the three spatial dimensions we experience. In these theories, gravity appears weak compared to the other fundamental forces because some of its effect leaks into these extra dimensions. If an incredibly advanced civilization could somehow access and manipulate these hidden dimensions, perhaps they could enhance or recreate gravitational effects in our three-dimensional space. Again, the gap between this theoretical possibility and any practical implementation is vast. Our current understanding of physics provides no clear path to accessing, let alone manipulating, any extra dimensions that might exist. One of the most speculative approaches would involve creating artificial mass or energy distributions throughout space to replace the gravitational influence of natural structures like planets and stars. Imagine a network of devices spread throughout a solar system, each capable of generating a tiny gravitational field. Working together, they might create a web of attraction that could approximate the effects of a planet's or star's gravity. The scale of such an undertaking would be staggering. To replace Earth's gravity alone would require technology capable of replicating the gravitational effect of an entire planet. To maintain anything resembling the current structure of a galaxy would require millions or billions of such devices spread across incomprehensible distances. Even if any of these approaches were technically feasible, they would face another fundamental challenge. In a universe without natural gravity, the cosmic dissolution we've described would happen rapidly, potentially outpacing any attempt to implement artificial solutions. Stars would explode or disperse within days or weeks. Planets would disintegrate over similar timeframes. The materials and energy sources needed to build gravity-generating technology would themselves be scattered across space before the technology could be deployed. This sobering reality suggests that any civilization hoping to survive gravity's disappearance would need to have artificial gravity technology already developed and ready to implement on a massive scale immediately. The window for response would be measured in hours or days, not years or decades. Perhaps the most realistic approach would be more modest in scope. Rather than trying to replace gravity throughout the cosmos, an advanced civilization might focus on creating localized regions where gravitational effects are simulated or artificially generated. These would not be meant to save the universe, but to serve as arcs, preserving small pockets of complexity in an increasingly disordered cosmos. Rotating habitats would be the most technically feasible option for such arcs. With sufficient advance warning, a civilization might construct fleets of massive rotating space habitats, stocked with diverse life forms and the technology needed to sustain them. These arcs would be designed to be as self-sufficient as possible, recycling air, water, and nutrients with minimal loss. Power would present a significant challenge for these habitats. Solar energy would become increasingly unreliable as stars dispersed and cooled. Nuclear energy, both fission and fusion, might provide power for centuries or millennia, but even these sources would face limitations in a universe where new fuel could not be easily acquired as natural processes of element creation in stars ceased. Even with the most optimistic assumptions about technology and preparation, such arcs would face inevitable decline. The laws of thermodynamics dictate that no closed system can maintain order indefinitely. Without the organizing influence of gravity to create new structures and energy gradients, even the most advanced artificial habitats would slowly run down as energy dispersed and materials degraded. The psychological aspects of such an existence would be equally challenging. Imagine living in a habitat you could never leave, knowing that outside its walls exists only an ever-expanding void, where the rich tapestry of cosmic structure once existed. The night sky, once filled with stars arranged in familiar constellations, would grow darker year by year as stars dispersed beyond the range of visibility. Eventually, nothing would be visible outside at all, just eternal blackness in every direction. How would consciousness itself fare in such conditions? Our minds evolved in a gravity-shaped environment, with up and down, mountains and valleys, oceans and shores. Our languages, metaphors, and ways of thinking are permeated with concepts that assume gravity's constant presence. Even our emotions reflect gravitational experience. We fall in love, rise to the occasion, sink into depression, feel uplifted or weighed down. A civilization living in artificial habitats after gravity's disappearance would likely develop new ways of thinking, new languages, and new metaphors reflecting their rotating environment. Children born in these habitats would have no direct experience of natural gravity, knowing it only through recordings and accounts from earlier generations. Over time, the memory of the gravity-shaped universe would fade, becoming first history, then legend, and perhaps eventually myth. Looking beyond the preservation of life and consciousness, could an advanced civilization attempt something even more ambitious, the recreation of gravity itself as a fundamental force? This question takes us to the very frontiers of theoretical physics and into realms that might better be described as philosophical than scientific. Some theories suggest that the fundamental constants and forces of our universe, including gravity, are not necessarily fixed but might have emerged from more fundamental processes during the universe's formation. If this were true, and if a civilization achieved a level of technology so advanced that it could manipulate the underlying structure of reality itself, perhaps it could induce the re-emergence of a gravity-like force. The energy and technology required for such an undertaking would be beyond astronomical, likely requiring the harnessing of energies comparable to that of the Big Bang itself. Whether any form of intelligence that evolved within our universe could ever achieve such capabilities remains an open question, one that perhaps takes us beyond the bounds of what we can meaningfully speculate about with our current understanding. What this exploration of artificial gravity reveals is both the ingenuity of the human mind in imagining solutions to even the most catastrophic scenarios, and the profound dependency of our existence on the natural laws and structures of the cosmos. We can simulate gravity's effects in limited ways, and perhaps an incredibly advanced civilization could do more, but nothing we can currently conceive of would truly replace gravity as a cosmic organizing principle. This realization returns us to a theme that has run throughout our exploration: gravity's role in creating the conditions for complexity and consciousness in the universe. The force we experience as weight, as the constant pull toward Earth's center, is the same force that shaped the cosmos from its earliest moments, enabling the emergence of structure, life, and ultimately minds capable of comprehending the universe itself. The artificial gravity technologies we've discussed, from rotating habitats to speculative gravity generators, might preserve small islands of order temporarily in a universe trending toward uniform disorder. But they would be just that, temporary preservations of complexity in a cosmos that had lost its fundamental architect. In this light, gravity appears not just as a force to be overcome or replicated, but as a gift to be appreciated, the cosmic principle that makes our existence possible. Without it, not even the most advanced technology we can imagine would maintain the universe's capacity for structure, complexity, and consciousness indefinitely. And so our exploration of artificial gravity brings us full circle to a deeper appreciation of the natural force that has shaped everything we know, from the ground beneath our feet to the stars overhead, from the structure of our bodies to the formation of our thoughts. In contemplating whether we could recreate gravity artificially, we discover how thoroughly natural gravity has created us. Our exploration has taken us through the cosmic consequences of gravity's disappearance, from the immediate effects on Earth to the ultimate dissolution of space-time itself. Now we turn to a deeper question. Why is gravity so fundamental to our universe? What makes this seemingly weakest of forces so crucial to the cosmos as we know it? To answer this, we must first understand gravity's unique place among the four fundamental forces of nature. These forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, together govern all interactions in the physical world. Yet gravity stands apart from the others in several profound ways. Unlike the other forces, gravity appears to be purely attractive. Electromagnetic forces can both attract and repel, depending on whether charges are opposite or alike. The nuclear forces have their own complex dynamics of attraction and repulsion at subatomic scales. Gravity, however, only pulls, never pushes. Every bit of mass or energy in the universe attracts every other bit, creating a web of interconnection that spans the cosmos. This universal attraction represents something profound about the nature of mass and energy. According to Einstein's famous equation, E equals mc squared, mass and energy are equivalent, different forms of the same fundamental substance. Gravity responds to both, with light being bent by massive objects despite photons having no rest mass. This relationship between gravity, mass, and energy points to something deeper about the fabric of reality itself. The attractive nature of gravity has philosophical implications as well. In a universe where other forces both attract and repel, creating balance through opposition, gravity stands as a force of pure connection. It draws things together across any distance, a cosmic principle of relationship that knows no boundaries or exclusions. Every particle in your body is attracted, however weakly, to every particle in the most distant galaxy we can observe. This universal connectedness through gravitational attraction provides a physical basis for the philosophical concept that all things in the cosmos are fundamentally interrelated. This universal attraction leads to another unique characteristic of gravity. It is cumulative and unlimited in range. The electromagnetic force weakens with distance, and the nuclear forces operate only at subatomic scales. But gravity, though it also weakens with distance, has no maximum range. Every object in the universe, no matter how distant, exerts some gravitational pull on every other object. This pull may become vanishingly small at great distances, but it never quite reaches zero. The mathematical expression of this relationship, Isaac Newton's inverse square law, tells us that gravity diminishes with the square of the distance between objects. Double the distance, and the force becomes 4 times weaker. Triple it, and the force is 9 times weaker. But crucially, it never disappears entirely. The gravitational influence of a single electron on the edge of the observable universe still reaches us here on Earth, though the effect is so minuscule as to be immeasurable. This infinite reach creates a cosmos where everything is connected to everything else, a web of influence that spans all of existence. The consequence of this unlimited range is that gravity dominates the large-scale structure of the universe. While other forces may be stronger in their domains, they tend to cancel out over cosmic distances. Positive and negative electric charges balance each other, creating electrically neutral objects at macroscopic scales. The nuclear forces remain confined within atomic nuclei. Gravity, however, simply adds up. The more mass gathered in one place, the stronger its gravitational pull becomes, allowing it to gather still more mass in a feedback loop that has shaped cosmic structure since the earliest moments after the Big Bang. This feedback process, sometimes called gravitational instability, represents one of the most important structure-forming mechanisms in the universe. Regions with slightly more matter than average exert slightly stronger gravitational pulls, drawing in additional matter from surrounding regions. This causes the density contrast to increase further, strengthening the gravitational attraction even more. Over cosmic time, this runaway process turns tiny fluctuations in the density of the early universe into the vast structures we see today: stars, galaxies, and the cosmic web of galaxy superclusters. Without this cumulative property of gravity, the universe would remain forever uniform, without the concentrations of matter and energy needed to form complex structures. This cumulative nature explains why gravity, despite being the weakest fundamental force by a staggering margin, ultimately determines the fate of stars, galaxies, and the universe itself. At the particle level, gravity is so weak that we can safely ignore it when describing how electrons orbit atomic nuclei or how protons and neutrons bind together. The electromagnetic force is about 10 to the power of 36 times stronger than gravity when comparing the attraction between two protons. Yet scale up to astronomical sizes, and gravity reigns supreme. To put this weakness in perspective, consider that a small toy magnet can lift a paperclip, overcoming the gravitational pull of the entire Earth. Your muscle power easily overcomes Earth's gravitational attraction when you lift an object, though Earth outweighs you by a factor of over 10 to the 20. A single electron feels an electromagnetic attraction to a proton that is roughly 1, followed by 40 zeros, times stronger than their mutual gravitational attraction. This extreme disparity in strength, often called the hierarchy problem, remains one of the great puzzles in physics, potentially pointing toward extra dimensions or entirely new principles yet to be discovered. The scales at which gravity operates contribute to its fundamental importance. Gravity is the only force that remains relevant from the smallest scales we can measure to the largest structures in the observable universe. It affects everything from the behavior of quantum particles to the evolution of galaxy superclusters spanning billions of light years. No other force bridges such an enormous range of scales. This remarkable range means that gravity connects phenomena across what physicists call many orders of magnitude, from the quantum realm to the cosmic. When we study black holes, we encounter regimes where quantum mechanics and gravity must both be taken into account, yet our current theories struggle to reconcile them. The search for a theory of quantum gravity represents one of the greatest challenges in modern physics, precisely because gravity alone spans these vastly different scales of reality, from the infinitesimal to the cosmic. Perhaps most profound is gravity's relationship with space-time itself. According to Einstein's general relativity, gravity is not a conventional force like the others, but a manifestation of space-time curvature. Mass and energy bend the fabric of space-time, and this bending guides the motion of other masses and energy, creating what we experience as gravitational attraction. This geometric view of gravity makes it uniquely woven into the very structure of reality, not merely a force operating within that structure. This geometric understanding represents one of the most beautiful and profound insights in the history of physics. In Newton's view, gravity was a mysterious force acting instantaneously across empty space, a concept Newton himself found philosophically troubling. Einstein reimagined gravity not as a force, but as a consequence of the shape of space-time itself. Massive objects create depressions in the fabric of space-time, like a bowling ball placed on a mattress. Other objects follow the curves created by these depressions, like marbles rolling on the mattress surface. What appears as an attractive force is actually the result of objects following the straightest possible paths through curved space-time. Gravity is not something added to reality, but is inherent in its very geometry, the shape of space and time themselves. This deep connection between gravity and space-time leads to phenomena unique among the fundamental forces. Gravitational waves, ripples in space-time itself, travel at the speed of light and carry energy across the cosmos. Black holes, regions where space-time is curved so severely that nothing can escape, represent the ultimate expression of gravity's power to shape reality. Gravitational time dilation, where time passes differently depending on the strength of the gravitational field, reveals that gravity affects not just space but time as well, binding the two together in the unified concept of space-time. The detection of gravitational waves by the LIGO and Virgo collaborations in recent years has opened an entirely new window on the universe. These ripples in space-time, caused by cataclysmic events like the collision of black holes or neutron stars, carry information across billions of light years, allowing us to observe phenomena that emit no light. The first detection, announced in 2016, confirmed a prediction Einstein had made a century earlier and provided the first direct observation of black holes. The objects so extreme, they can only be understood through gravity's effect on the fabric of reality itself. Time dilation, where clocks run at different rates depending on the strength of the gravitational field they experience, has practical consequences in our daily lives. The GPS system that guides our cars and phones must account for the fact that atomic clocks on satellites run slightly faster than identical clocks on Earth's surface due to the weaker gravitational field in orbit. Without these relativistic corrections, GPS positions would drift by about 10 kilometers each day, rendering the system useless. Each time we navigate with our phones, we are making practical use of the fact that gravity curves not just space but time itself. Beyond these physical characteristics, gravity plays an essential role in creating the conditions necessary for complexity to arise in the universe. Without gravity, matter would remain forever dispersed, never concentrating sufficiently for stars to form. Without stars, the heavier elements necessary for planets and life would never be forged through nuclear fusion. Without planets, stable environments where complex chemistry could evolve into biology would not exist. Consider the remarkable sequence that gravity makes possible. In the early universe, matter was distributed almost uniformly, with only tiny fluctuations in density. Gravity amplified these fluctuations, drawing matter into denser regions and away from less dense ones. Eventually, clouds of hydrogen and helium became dense enough for their cores to reach the temperatures and pressures needed for nuclear fusion. Stars were born, creating not just light and heat but also the heavy elements necessary for rocky planets and complex chemistry. These elements, scattered into space by supernovae and planetary nebulae, were eventually incorporated into new star systems with planets. On at least one such planet, complex chemistry evolved into life, which eventually developed sufficient complexity for consciousness to emerge. Each step in this sequence depends critically on gravity's, ability to concentrate matter against the general expansion of the universe. Without it, reality would remain forever simple, dispersed, and unconscious. The story of cosmic evolution, from the primordial hydrogen clouds after the Big Bang to the rich diversity of structures we observe today, is largely a story of gravity patiently drawing matter together against the universe's overall expansion. Gravity creates the non-uniform distribution of matter and energy that enables complex systems to emerge, from galaxies to living cells. This process operates hierarchically, with gravity creating structure at each level. First come galaxy clusters and superclusters, spanning hundreds of millions of light years. Within these form individual galaxies, ranging from dwarfs a few thousand light years across to giants spanning hundreds of thousands of light years. Galaxies fragment into star clusters and molecular clouds, which in turn collapse to form individual stars and their planetary systems. Around suitable stars, planets form at distances that allow for liquid water and stable conditions conducive to life. All of this nested complexity emerges from the relentless pull of gravity, creating local concentrations of matter and energy within an otherwise expanding universe. Consider how gravity enables the existence of stable energy sources like stars. A star represents a delicate balance between the inward pull of gravity, which would collapse the star if unopposed, and the outward pressure generated by nuclear fusion at the core. This balance can persist for billions of years, providing the steady energy output that makes life possible on planets like Earth. Without gravity, fusion might still occur, but it would not be contained in stable, long-lived structures that can nurture life on orbiting worlds. This stellar balance between gravitational collapse and fusion pressure represents one of the most important equilibrium states in the cosmos. Too much gravity, more mass, and a star burns its fuel too quickly, living a brief life measured in millions rather than billions of years, potentially too short for complex life to evolve on its planets. Too little gravity, less mass, and nuclear fusion occurs at a slower rate, creating less heat and light. Our Sun represents a middle way, massive enough to generate sufficient energy for life, but not so massive that it exhausts its fuel too quickly. This balance gives planets like Earth stable conditions over the billions of years needed for complex life to evolve. Gravity does not just create stars, it creates stars with lifetimes conducive to the emergence of complexity and consciousness on their orbiting worlds. Gravity also creates the conditions for element formation beyond hydrogen and helium. In the cores of massive stars, gravitational pressure drives fusion reactions that forge progressively heavier elements up to iron. When these stars die in supernova explosions, gravitational collapse plays a crucial role in creating the conditions where elements heavier than iron can form. Without these heavier elements, the complex chemistry needed for life as we know it would be impossible. The periodic table of elements, with its rich diversity of atomic structures and chemical properties, is largely a product of gravity's influence. The Big Bang produced primarily hydrogen and helium, with only trace amounts of lithium and beryllium. All heavier elements, from the carbon in our cells, to the oxygen we breathe, to the iron in our blood, were forged in stars or during their explosive deaths. Gravitational pressure creates the extreme conditions needed for nuclear fusion to overcome the electrostatic repulsion between atomic nuclei, forcing them close enough together for the strong nuclear force to bind them. The gold in a wedding ring, the calcium in our bones, the silicon in computer chips, all owe their existence to gravity's role in stellar evolution. On planetary scales, gravity shapes environments conducive to life in countless ways. It holds atmospheres in place, allowing for weather patterns that distribute water and heat. It drives the convection currents in Earth's mantle that recycle surface materials through plate tectonics, maintaining the chemical balance needed for a stable biosphere over geological timescales. It creates tides that shaped coastal ecosystems and may have played a role in life's transition from sea to land. Consider Earth as a case study in gravity's life-enabling influence. With just the right mass, our planet maintains an atmosphere dense enough to support liquid water, but not so dense as to create crushing pressure or runaway greenhouse effects like on Venus. This atmosphere provides protection from cosmic radiation and meteorites, regulates temperature, distributes moisture, and transports the gases needed for life. Gravity drives the internal heat engine that powers plate tectonics, which in turn recycles carbon between the atmosphere and the planet's interior, regulating global temperatures over geological timescales. The gravitational dance between Earth and Moon creates tides that may have provided the fluctuating conditions where life first emerged, with tidal pools repeatedly concentrating chemicals, then dispersing them, potentially catalyzing the first self-replicating systems. From global climate to local weather, from the shape of continents to the flow of rivers, gravity shapes the stage upon which the drama of life unfolds. Even within living organisms, gravity provides a consistent reference frame that guides development and function. Seeds know which way to send roots and shoots because gravity tells them which way is down. Animal bodies develop with bilateral symmetry, partly in response to the unidirectional pull of gravity. Our sense of balance, our cardiovascular systems, our muscular and skeletal structures, all evolved with gravity's constant influence as a fundamental parameter. The gravitropic response in plants represents one of the most remarkable adaptations to gravity's influence. Place a seed in soil in any orientation, and its root will find its way downward while its shoot grows upward. This guidance comes from specialized cells containing dense starch grains that settle to the bottoms of cells under gravity's influence, triggering hormonal responses that direct growth. Animals similarly use gravity as a reference frame, with specialized organs like the vestibular system in our inner ear detecting orientation relative to Earth's gravitational field. The very shapes of our bodies, with legs beneath torsos, heads atop necks, and internal organs arranged from top to bottom, all reflect adaptation to life in a gravitational field. Even our perception and cognition are influenced by gravity, with concepts like up and down deeply embedded in our thinking, language, and emotional associations. We fall in love, feel uplifted by good news, sink into depression, rise to challenges, and get grounded in reality, all metaphors derived from our experience of gravity's constant presence. The relationship between gravity and the other fundamental forces reveals further aspects of its special nature. While physicists have made progress in unifying the electromagnetic force with the weak and strong nuclear forces in what is known as the Standard Model, gravity has resisted incorporation into this framework. This resistance suggests that gravity may be fundamentally different from the other forces in ways we do not yet fully understand. One key difference lies in how gravity behaves at quantum scales. The other three forces have been successfully described using quantum field theory, which treats forces as arising from the exchange of carrier particles or bosons. Electromagnetism works through the exchange of photons. The weak nuclear force operates via W and Z bosons. The strong force functions through gluons. Each of these carrier particles has been experimentally observed, confirming major aspects of the Standard Model. Gravity, if it follows similar principles, should operate through the exchange of hypothetical particles called gravitons. However, no one has ever observed a graviton, and there are theoretical reasons to believe they might be extraordinarily difficult to detect. The quantum theory of gravity remains one of the great unsolved problems in modern physics, with approaches like string theory and loop, quantum gravity, offering potential but as yet unverified solutions. The search for gravitons and a quantum theory of gravity highlights the profound difference between gravity and the other forces. The others can be quantized because they operate within space-time as fields that permeate it. Gravity, however, is space-time itself, or at least its curvature. Attempting to quantize gravity means attempting to quantize the very arena in which quantum events occur, a conceptual challenge that has resisted solution for nearly a century. The most promising approaches suggest radical revisions to our understanding of space and time at the smallest scales, with discrete units of space-time or extra dimensions curled up to microscopic size. If such theories prove correct, our most fundamental concepts of reality may need revision, all because gravity's unique nature forces us to reconsider what space and time actually are. This difficulty in quantizing gravity points to its unique relationship with space-time. The other forces operate within space-time, while gravity, according to general relativity, is space-time, or at least an aspect of its curvature. This fundamental difference may explain why gravity does not fit neatly into the quantum framework that works so well for the other forces. The boundary between general relativity and quantum mechanics represents perhaps the most important frontier in theoretical physics. In most situations, we can use one theory or the other, depending on the scale of the phenomena involved. But at the edge of a black hole, or in the first moments after the Big Bang, both theories should apply simultaneously, yet they give incompatible answers. This suggests that a deeper theory awaits discovery, one that might revolutionize our understanding of reality as profoundly as quantum mechanics and general relativity did in the early 20th century. The unique nature of gravity, as both a force and the geometry of space-time itself, stands at the center of this theoretical challenge. At the largest scales, gravity creates the cosmic web, that vast network of galaxy filaments and clusters separated by enormous voids. This structure provides the framework within which all smaller-scale cosmic processes unfold. The variations in density throughout this web create distinct environments where different types of galaxies form, influencing the types of stars and planetary systems that emerge within them. This cosmic web spans billions of light-years, yet its overall structure resembles patterns seen in many natural systems, from the neurons in our brains to the mycelium networks of fungi to the branching of trees and rivers. Such similar patterns emerging at widely different scales and in vastly different systems suggest a fundamental organizing principle at work. For the cosmic web, that principle is gravity, drawing matter into filaments along paths of least resistance between density peaks, while leaving other regions relatively empty. The resulting structure, with its characteristic filaments, nodes, and voids, represents perhaps the largest pattern in nature, an organization that would be impossible without gravity's influence over cosmological distances. The way gravity shapes galactic evolution reveals its patient, cumulative nature. Over billions of years, gravity guides the dance of galaxies, causing them to orbit one another, collide and merge, and sometimes tear each other apart through tidal forces. Our own Milky Way has grown largely by consuming smaller galaxies, a process that continues today and will culminate billions of years in the future when our galaxy merges with the neighboring Andromeda galaxy. This slow restructuring of the cosmos through gravitational interaction creates the conditions for new stars to form and old ones to die, maintaining the cosmic cycles that ultimately make life possible. Our galaxy's history illustrates this process. The Milky Way has not existed unchanged since its formation, but has grown through repeated mergers with smaller galaxies. The halo of older stars surrounding the galactic disk contains the remains of dwarf galaxies consumed over billions of years. Currently, the Milky Way is in the process of devouring several smaller satellite galaxies, including the Sagittarius dwarf spheroidal galaxy, whose stars are being stretched into a long stream as it is torn apart by our galaxy's gravitational field. About 4.5 billion years from now, the Andromeda galaxy, currently 2.5 million light-years away, will collide with our own, triggering new waves of star formation as gas clouds are compressed. Over time, the two spiral galaxies will merge into a single elliptical galaxy, a transformation driven entirely by gravitational interaction. Throughout the universe, similar processes of collision, merger, and tidal disruption continually reshape galaxies, all choreographed by gravity's influence. Gravity also plays a crucial role in regulating star formation within galaxies. As giant molecular clouds collapse under their own weight, they fragment into smaller clumps that eventually become individual stars. The mass of these stars, determined largely by how much material gravity can gather before stellar winds blow the rest away, establishes their life cycles, from the brief, brilliant lives of massive blue stars to the trillion-year slow burn of the smallest red dwarfs. This variety in stellar types creates diverse planetary systems and opportunities for life to emerge in different environments. The process of star formation beautifully illustrates gravity's creative role. Interstellar gas clouds, left to themselves, would remain diffuse for billions of years, held apart by their internal pressure and random thermal motion. Gravity overcomes this resistance, drawing the gas molecules together until density and temperature become high enough for nuclear fusion. Yet gravity does not simply create a uniform collapse. Small initial variations in density cause the cloud to fragment into many individual stars of different masses. This fragmentation process, driven by gravity but moderated by other factors like rotation, turbulence, and magnetic fields, creates the diverse stellar populations observed in galaxies. Some stars form in isolation, others in binary or multiple systems, still others in dense clusters. Some are massive and short-lived, others small and long-lasting. This diversity, created by the interplay between gravity and other forces, increases the variety of environments where life might potentially emerge. Within our own solar system, gravity's organizing influence manifests in countless ways. The distinctly different worlds of the inner and outer planets reflect gravity's role in the solar system's formation, with the sun's gravity holding the inner rocky worlds close, while allowing the gas giants to form in the colder outer regions. The asteroid belt exists largely because Jupiter's gravity prevented a planet from forming there, instead stirring up the region so effectively that the material could never coalesce. The Kuiper belt and Oort cloud, those distant reservoirs of icy bodies, are structured by the combined gravitational influence of the Sun, the planets, and even passing stars, and the Milky Way itself. The solar system's architecture demonstrates gravity's role as cosmic sculptor. During formation, the protoplanetary disk around our young Sun was compositionally segregated by temperature, with only rocky materials able to condense in the hot inner regions, while ices could form in the cooler, outer regions. Gravity gathered these materials into planets, with the inner worlds built primarily from rock and metal, while the outer planets could accumulate vast amounts of hydrogen and helium around rocky cores, becoming the gas giants we see today. Jupiter, the largest planet, formed early enough to dramatically influence the rest of the system's development. Its gravity prevented a planet from forming where the asteroid belt now exists, captured numerous asteroids into stable orbits as its Trojan companions, and likely played a role in scattering water-rich asteroids and comets into the inner solar system, potentially delivering Earth's water. Even the orbits of the planets, nearly circular and aligned in the same plane, reflect the organizing influence of gravity during the solar system's formation. What might have been a chaotic assortment of debris became, through gravity's influence, an ordered system of planets orbiting in stable, nearly circular paths that have persisted for billions of years. What makes gravity truly fundamental, then, is not merely its role as one of the four basic forces, but its unique capacity to create order and structure across all scales of the universe. While the other fundamental forces enable the interactions that constitute complex systems, gravity provides the framework within which those systems can form and persist. This ability to create ordered structures across such a vast range of scales sets gravity apart from the other forces. The strong nuclear force, though incredibly powerful, operates only within atomic nuclei, binding quarks into protons and neutrons, and these nuclei into atoms. The weak nuclear force, responsible for certain types of radioactive decay, similarly functions only at subatomic scales. The electromagnetic force, while having unlimited range like gravity, tends to cancel itself out at larger scales because positive and negative charges balance each other. Only gravity, with its purely attractive nature and unlimited range, can create ordered structures from the size of planets to galaxy superclusters spanning billions of light years. This unique capacity makes gravity the primary architect of cosmic structure. In a very real sense, gravity is the force that fights against cosmic entropy, the tendency of the universe toward increasing disorder. The second law of thermodynamics tells us that closed systems inevitably become more disordered over time. Yet gravity works against this trend, gathering diffuse matter into concentrated structures, creating energy gradients that can drive complex processes, forming pockets of increasing order even as the universe as a whole tends toward disorder. This counterentropic role represents perhaps gravity's most profound significance. The universe began in a state of extraordinarily high temperature and nearly uniform density. According to the second law of thermodynamics, it should have progressed toward ever greater disorder, with matter and energy spreading ever more evenly throughout space. Indeed, the universe's overall evolution follows this pattern, with entropy increasing over cosmic time. Yet within this general trend toward disorder, gravity creates local regions of increasing order and complexity. By drawing matter together against its tendency to disperse, gravity creates the conditions for stars, planets, and ultimately life to emerge. These ordered structures do not violate the second law, as the increase in entropy elsewhere particularly through the heat and radiation stars emit, more than compensates for the local decrease in entropy they represent. Nevertheless, without gravity's counterentropic influence, the universe would remain forever simple, a uniform soup of elementary particles, gradually cooling as space expands, without the concentrations of matter and energy needed for complexity to emerge. This counter-entropic role makes gravity essential, not just for the existence of stars, planets, and living beings, but for the very possibility of complexity itself. In a universe without gravity, entropy would reign unopposed, with matter and energy dispersing ever more uniformly throughout space. No structures more complex than individual atoms or molecules could form or persist, and even these would be scattered so widely that interactions between them would become vanishingly rare. The concept of complexity itself, with its nested hierarchies and emergent properties, depends on gravity's ability to concentrate matter against entropy's dispersive tendency. Complex systems require energy flows to maintain their organization, and these flows depend on energy gradients created primarily by gravity. The temperature difference between a star's core and its surface, the potential energy of water at higher elevations, the chemical energy stored in fossil fuels, formed in ancient ecosystems powered by sunlight, all these energy sources that drive complex systems ultimately depend on gravity's organizing influence. Without these energy gradients, complex systems cannot form or persist. In this sense, complexity itself is a phenomenon made possible by gravity's unique properties. Gravity's influence extends even to the quantum realm, though its effects there are typically too weak to measure directly. Theoretical work suggests that gravity plays a role in the decoherence process, whereby quantum systems that exist as superpositions of multiple states collapse into single definite states when they interact with their environments. Some models propose that the gravitational interaction between different possible configurations of mass might contribute to this collapse, potentially connecting gravity to one of the most profound mysteries in quantum mechanics. This potential link between gravity and quantum decoherence represents one of the most intriguing frontiers in physics. According to one hypothesis, quantum superpositions of significantly different mass distributions would create different gravitational fields. These different fields would interact with the environment in detectably different ways, essentially leaking information about the system's state into the environment and causing decoherence. If this hypothesis proves correct, gravity may play a fundamental role in the emergence of the classical world from quantum foundations, the process by which the probabilistic, wave-like behavior of quantum systems gives way to the definite, particle-like behavior we observe at macroscopic scales. This would represent yet another way in which gravity shapes the emergence of complexity from simplicity, the transition from the quantum realm of possibilities to the classical realm of actualities. Theoretical physicists have long sought a grand unified theory that would bring gravity together with the other fundamental forces, revealing them all as different aspects of a single underlying principle. So far, this unification has proven elusive. Quantum theories that successfully describe the other three forces have been difficult to reconcile with general relativity's geometric description of gravity. This challenge suggests that gravity's unique nature may reflect something profound about the structure of reality that we have yet to fully comprehend. This quest for unification has led to some of the most ambitious and mathematically sophisticated theories in physics. String theory proposes that all particles are actually tiny vibrating strings, with different vibration patterns creating different particles. The theory naturally incorporates gravity through the graviton, a particular vibration mode of these strings. However, it requires additional spatial dimensions beyond the three we experience, curled up to microscopic size. Loop quantum gravity takes a different approach, suggesting that space-time itself has a discrete, quantum structure at the smallest scales, like pixels in a digital image. Other approaches, like causal set theory or asymptotic safety, offer alternative paths toward reconciling gravity with quantum principles. Despite decades of effort by some of the world's most brilliant minds, none of these approaches has yet produced a complete, experimentally verified theory of quantum gravity. This persistent challenge suggests that we may be missing something fundamental about the nature of reality, with gravity pointing toward principles beyond our current understanding. Some theories propose that gravity might be an emergent phenomenon rather than a truly fundamental force, arising from deeper quantum mechanical processes rather than being elementary itself. Others suggest that gravity might operate differently at quantum scales or in extra dimensions beyond the three spatial dimensions we experience directly. Regardless of which theoretical approach ultimately proves correct, gravity's role in shaping our universe remains undeniable. The concept of gravity as an emergent phenomenon, rather than a fundamental force, represents one of the most radical reconsiderations of this force. According to some theoretical approaches, gravity might not be a force or field in the same sense as electromagnetism or the nuclear forces. Instead, it might be a statistical or collective effect arising from the behavior of more fundamental entities, similar to how temperature emerges from the collective motion of molecules rather than being a fundamental property itself. In such theories, space-time and its curvature would not be fundamental, but would emerge from more basic quantum processes. This perspective represents a profound inversion of our usual thinking, with space-time itself becoming a derivative rather than foundational concept. If true, gravity would not be one of the basic forces of nature, but rather a consequence of more fundamental quantum processes, a macroscopic manifestation of microscopic reality rather than a basic constituent of that reality. The relationship between gravity and consciousness presents another profound connection. Consciousness, that mysterious capacity for subjective experience and awareness, emerges from the complex organization of matter in brains. This organization depends on energy flows and information processing that would be impossible without the stable, structured environments gravity creates. More fundamentally, the arrow of time that gives experience its direction and meaning arises from the entropy gradient created in part by gravity's ability to generate local order. In this sense, gravity creates not just the physical conditions for consciousness, but the temporal framework within which awareness unfolds. This connection between gravity and consciousness highlights the force's fundamental role in creating the conditions for complexity. Our brains, perhaps the most complex structures we know of in the universe, require an extraordinary degree of organization, with approximately 86 billion neurons forming trillions of connections. This organization depends on energy flows that ultimately trace back to the sun, where gravity maintains the conditions for nuclear fusion. The stable planetary environment that allows brains to evolve and function depends on Earth's gravity holding our atmosphere and regulating our climate. The arrow of time that gives our experiences their sequential nature, with memories of the past but not the future, depends on the entropy gradient that gravity helps create by forming ordered structures against the universe's overall trend toward disorder. Even the emergence of life itself, a prerequisite for consciousness, depends on gravity creating stable planetary environments where chemistry can evolve toward biology. In this chain of dependencies, gravity stands as the first link, the force without which consciousness as we know it could not exist. As we reflect on why gravity is fundamental, we are drawn to a striking parallel between gravity's role in the cosmos and the concept of relationship itself. Just as gravity connects every particle to every other particle across the vast reaches of space, relationships connect every entity to others, creating webs of meaning and significance. Gravity might be seen as the physical embodiment of the principle that nothing in the universe exists in true isolation, that everything is connected to everything else in a great cosmic web of mutual influence. This metaphorical connection between gravity and relationship offers a profound way of understanding our place in the cosmos. We often think of objects as primary and relationships as secondary, the connections between already existing things. But gravity suggests a different perspective, where relationship is primary and objects emerge from their web of connections. A star exists as a star because of its gravitational relationship with its own matter and with the planets orbiting it. A galaxy exists as a galaxy because of the gravitational relationships among its stars, gas clouds, and dark matter. Even space-time itself, according to general relativity, is not a fixed backdrop, but a dynamic web of relationships, with each mass influencing the geometry around it, which in turn influences the motion of other masses. In this view, our own existence is similarly relational, emerging from the connections we have with the world around us, from the molecular relationships within our cells, to the social relationships within our communities, to the gravitational relationship between our bodies and the earth beneath our feet. This perspective invites us to see gravity not merely as a force to be measured and calculated, but as a principle to be contemplated and appreciated. The same force that keeps our feet on the ground also binds the stars in their courses and shapes the evolution of the universe itself. In its patient gathering together of matter, in its creation of structure from uniformity, in its nurturing of the conditions where complexity and consciousness can emerge, gravity reveals itself as perhaps the most fundamental principle in a universe of wonders. Gravity teaches us that we exist not as isolated entities, but as participants in a cosmic web of relationship that spans scales from the quantum to the cosmological. The atoms in our bodies were forged in stars and distributed through space by gravitational processes. Our planet formed through the gravitational accretion of countless smaller bodies. Our weight, our sense of up and down, our weather patterns, our ocean currents, all exist because of Earth's gravitational relationship with us, with our atmosphere, with our oceans, and with the sun. Even our consciousness, that seemingly most personal and interior aspect of our existence, depends on the brain's complex organization, which in turn depends on energy flows and stable conditions made possible by gravity's organizing influence. We are not just on Earth, we are of Earth, shaped by the same gravitational processes that formed our planet and sustain its dynamics. And so we come to understand that, in a universe without gravity, we would lose not just the ground beneath our feet, but the very possibility of existence as we know it. The disappearance of gravity would mean not just the end of our world, but the end of worlds altogether, a universe without structure, without history, without the capacity for telling its own story through the emergence of conscious beings. Gravity, in this light, appears not as a constraint to be overcome, but as the foundation upon which all else. Throughout our exploration of a universe without gravity, we have treated the scenario as a thought experiment, a hypothetical impossibility that nonetheless reveals profound truths about the cosmos we inhabit. But now we must ask a more unsettling question. Could gravity ever actually fail? Is there any scenario, however improbable, in which the force that shapes our universe might cease to operate, as it has since the beginning of time? From our current understanding of physics, the answer appears to be no. Gravity seems to be woven into the very fabric of space-time itself, not a force that can be switched on or off like a light. It is a fundamental property of mass and energy, an intrinsic aspect of existence as we understand it. For gravity to fail would require not just a change in the laws of physics, but a complete rewriting of reality at its most basic level. However, theoretical physics has occasionally suggested possibilities, if not for gravity's complete disappearance, then at least for significant modifications to how it operates under certain conditions. Let us explore some of these speculative ideas, keeping in mind that they remain at the frontiers of physics, more mathematical possibilities than established science. One area of theoretical exploration involves the concept of modified gravity theories. These propose that under certain conditions, typically at very large cosmic scales or very small quantum scales, gravity might behave differently than Einstein's general relativity predicts. Such theories were initially developed to explain phenomena like the apparent acceleration of the universe's expansion without invoking dark energy, or to account for galactic rotation curves without requiring dark matter. In some of these models, gravity could become repulsive rather than attractive at certain scales, or its strength might vary depending on the environment. While these modifications would not constitute a complete failure of gravity, they would represent significant departures from our current understanding. So far, however, observational evidence favors standard general relativity, with these modified theories remaining largely speculative. Another theoretical approach comes from the concept of brane cosmology, derived from string theory. In these models, our observable universe exists on a three-dimensional membrane, or brane floating within a higher dimensional bulk space. One of the most provocative suggestions from brane theory is that gravity, unlike the other fundamental forces, might leak into these extra dimensions, explaining why it appears so much weaker than the other forces in our three-dimensional experience. If this model were correct, it raises a highly speculative possibility. Could there be circumstances under which gravity might leak more dramatically into these extra dimensions, effectively draining away from our brain. While there is no established theoretical framework for such a catastrophic leakage, the mere existence of extra dimensions would introduce uncertainties about gravity's long-term stability in our observable universe. Quantum theories of gravity introduce other speculative possibilities. In approaches like loop quantum gravity, space-time itself emerges from more fundamental quantum structures. If these quantum foundations were somehow altered or destabilized, could the emergent property we experience as gravity be affected? Again, there is no clear theoretical path to such a scenario, but the incomplete state of quantum gravity theories leaves room for speculation. Some more exotic theories propose that the fundamental constants of nature, including the gravitational constant that determines gravity's strength, may not be truly constant, but could vary across time or space. Evidence strongly suggests these constants have remained stable throughout observable cosmic history, but some theories suggest they might change under extreme conditions or over enormously long timescales. If the gravitational constant were to gradually approach zero, for instance, the effects would initially be subtle, but would eventually lead to consequences similar to those we've explored in our thought experiment. Stars would begin to expand as the inward pressure of gravity weakened. Planetary orbits would gradually widen. Galaxies would start to dissolve as their stars drifted apart. The changes would occur so gradually that life might have time to adapt initially, but eventually, the conditions for complex structures would disappear. Even more speculative are scenarios involving concepts like vacuum decay. Some quantum field theories suggest that our universe might exist in a metastable state, rather like water that has been supercooled below its freezing point without turning to ice. In such models, a quantum fluctuation could potentially trigger a phase transition, a bubble of new vacuum that would expand at the speed of light, potentially altering the fundamental forces, including gravity, within the region it encompasses. These theoretical possibilities, while fascinating, remain firmly in the realm of speculation. No observational evidence suggests that gravity has ever operated differently throughout the universe's history, nor that any of these exotic scenarios is likely to occur. The stability of gravity is one of the universe's most dependable features, having shaped cosmic evolution consistently for nearly 14 billion years. Indeed, the evidence points overwhelmingly toward gravity's reliability. Observations of distant galaxies show that gravity operated the same way billions of years ago as it does today. Studies of primordial nucleosynthesis, the formation of light elements in the early universe, confirm that gravity behaved consistently even in the universe's infancy. Gravitational lensing, the bending of light around massive objects, works exactly as Einstein's theory predicts across cosmic scales. Even in the most extreme environments we can observe, such as the vicinity of black holes or the collision of neutron stars that produce gravitational waves, gravity follows the equations of general relativity with remarkable precision. These observations place stringent limits on how much gravity could possibly vary without our noticing, and so far, no variations have been detected despite increasingly sensitive measurements. What about the far future? Could gravity eventually fail as the universe continues to evolve? Current models of cosmic evolution suggest several possible fates for our universe, none of which involve gravity simply disappearing, but some of which would dramatically transform gravity's role. If the universe continues to expand at an accelerating rate, as current observations suggest, we may be headed for a big freeze or heat death scenario. In this future, galaxies beyond our local group would eventually recede beyond our observable horizon. Stars would burn out. Black holes would slowly evaporate through Hawking radiation. Matter would become increasingly dispersed. Gravity would still exist, but with ever less matter in proximity to be affected by it, its influence would become less and less relevant to an increasingly empty cosmos. Alternatively, if dark energy were to change its behavior in the future, the universe might experience a big rip. In this scenario, the accelerating expansion becomes so extreme that it eventually overcomes even the strongest forces, including gravity. Galaxies would be torn apart, followed by solar systems, planets, and eventually even atoms themselves. This would not represent a failure of gravity per se, but rather dark energy overwhelming gravity's binding force at all scales. A third possibility, considered much less likely based on current observations, is that the universe might eventually stop expanding and begin to contract, leading to a big crunch. In this scenario, gravity would become increasingly dominant as matter was compressed into smaller volumes, potentially culminating in a singularity similar to the one from which the Big Bang emerged. Some theories suggest this could even lead to a new universe being born, a concept known as the Big Bounce. None of these scenarios involves gravity failing in the sense we've explored in our thought experiment. Rather, they represent different possible outcomes of the ongoing interaction between gravity and other cosmic forces, particularly dark energy, whatever it may be. The remarkable stability of gravity across cosmic history and throughout the observable universe suggests that its complete failure would require something beyond the physics we currently understand. Yet the history of science teaches us humility. Our understanding of the cosmos has been repeatedly revolutionized by new observations and theoretical insights. What seems impossible within one framework may become comprehensible within another. Perhaps the most profound realization is that we cannot entirely rule out scenarios we cannot yet imagine. The frontiers of theoretical physics, where concepts like string theory, quantum gravity, and multiverse hypotheses are explored, continually open new possibilities that stretch our understanding of reality. In these uncharted territories, questions about the fundamental nature and stability of gravity remain open to speculation. What if, for instance, our universe is just one bubble in a vast multiverse, each bubble potentially operating under different physical laws? Could there be regions where gravity simply doesn't exist or works in ways we would not recognize? While such ideas remain highly speculative and possibly untestable, they remind us of the potential limits of our current understanding. Or consider the philosophical implications of simulation theories, which propose that our experienced reality might be a sophisticated computational construct. If true, gravity would be just another algorithm in the program, potentially subject to modification or termination by whatever or whoever might control the simulation. While such scenarios may seem more like science fiction than science, they highlight how fundamental assumptions about reality might be questioned at the deepest levels. Returning to more established physics, we might ask whether gravity's apparent stability throughout cosmic history guarantees its future reliability. Many physical systems that appear stable over long periods can reach tipping points where dramatic changes occur suddenly. Could gravity, or the cosmic conditions that allow it to operate as it does, potentially reach such a tipping point? Current physics offers no mechanism for such a phase transition affecting gravity itself, but again, our understanding continues to evolve. Amidst all this speculation, we should not lose sight of what current science tells us most clearly. Gravity has been a constant companion to the cosmos since its earliest moments, and shows every sign of remaining so for the foreseeable future. The scenarios we've explored where gravity might change or fail remain firmly in the realm of thought experiments rather than plausible predictions. Yet, these thought experiments serve a valuable purpose. By imagining the unimaginable, by asking what would happen if a fundamental assumption of our reality were suddenly changed, we gain a deeper appreciation for how that assumption shapes everything we know. Our journey through a gravitationless universe has revealed how profoundly this force influences every aspect of existence, from the largest cosmic structures to the most intimate biological processes. It has shown us that gravity is not merely a force that keeps us grounded, but a principle that enables the very possibility of structured complexity, of planets and stars, of life and consciousness. If there is a lesson in our speculation about gravity's potential failure, it is perhaps this: the aspects of reality we take most for granted, the constants that seem most reliable and unchanging, are often those whose influence is most pervasive and profound. Only by imagining their absence can we truly appreciate their presence. And so we conclude our exploration of whether gravity could ever actually fail, with a recognition of both the limits of our knowledge and the solid ground of our understanding. From all we currently know, gravity remains one of the most fundamental and stable aspects of our universe, likely to continue shaping cosmic evolution long after our brief moment in time has passed. Yet, in acknowledging the frontiers of our understanding, we keep open the sense of wonder and possibility that drives science itself forward, always seeking deeper insights into the nature of reality. The universe, after all, has surprised us before and will likely surprise us again. Our theories evolve, our understanding deepens, and what once seemed impossible sometimes becomes comprehensible. In that spirit of humble inquiry, we leave our question not entirely closed, recognizing that the final chapters of gravity's story, like many in science, remain to be written by future generations of exploration and discovery. As we near the conclusion of our journey through a universe without gravity, we turn to a dimension that transcends the purely physical. Beyond atoms and galaxies, beyond space-time itself, lies the realm of meaning, metaphor, and human experience. How has gravity, this most fundamental force, shaped not just our bodies but our minds, our languages, our very sense of what it means to be human? The influence of gravity on human thought begins with our earliest experiences. A child learning to stand and walk does so in direct negotiation with gravity's pull. Each tentative step, each fall and recovery, teaches profound lessons about effort, persistence, and the nature of the physical world. Before we have words, we understand through our bodies that the world has direction, that up differs fundamentally from down, that effort is required to rise and inevitable in falling. These embodied experiences become the foundation for language and metaphor. Consider how thoroughly gravitational concepts permeate our speech, often in ways we barely notice. We speak of feeling down when sad or up when happy. We rise to the occasion or fall from grace. We have grounded personalities or flighty imaginations. We are uplifted by good news or dropped into despair by bad. We fall in love, our hearts sink, our spirits soar. The philosopher George Lakoff and linguist Mark Johnson have written extensively about these embodied metaphors, arguing that our most abstract concepts are rooted in physical experiences, particularly those related to bodily orientation in space. Gravity, as the ever-present force that establishes this orientation, becomes the silent partner in much of our abstract thinking. Good is up, bad is down. More is up, less is down. Rational is up, emotional is down. These associations appear across cultures and languages, suggesting a deep connection between our physical experience of gravity and our conceptual understanding of the world. Our moral vocabulary similarly draws on gravitational metaphors. We speak of high standards and low behavior, of rising above base instincts, or being dragged down by temptation. The very concept of transcendence implies upward movement, an overcoming of the forces that hold us down. Heaven traditionally resides above, hell below. Angels fly upward while demons drag downward. These spatial orientations are not arbitrary, but reflect the embodied experience of effort against gravity as a metaphor for moral struggle. This connection between physical and moral elevation appears across diverse religious traditions. Mountains often serve as sacred sites, places where heaven and earth meet, where seekers climb physically upward as a parallel to spiritual ascent. Think of Mount Sinai, where Moses received the Ten Commandments, Mount Olympus, where Greek gods dwelled, or Mount Kailash, sacred to Hindus, Buddhists, and Jains alike. The physical effort of climbing against gravity becomes a metaphor and practice for spiritual elevation. Gravity shapes not just our metaphors but our aesthetic sense as well. In architecture, we admire structures that seem to defy gravity, from the soaring Gothic cathedrals of medieval Europe to the impossibly cantilevered modern skyscrapers of Dubai or Shanghai. Part of their beauty lies precisely in the tension between their apparent weightlessness and our embodied knowledge of gravity's relentless pull. Without gravity, such achievements would lose their power to awe us. In dance, the negotiation with gravity creates much of the art form's expressive power. A leaping dancer momentarily transcends earthly constraints, creating a visual metaphor for freedom, joy, or transcendence. The controlled descent that follows can express acquiescence, sorrow, or surrender. The most skilled dancers play with our expectations about gravity's effects, seeming to float, hover, or move in slow motion, creating emotional effects precisely through their manipulation of our gravitational expectations. Music, too, incorporates gravitational metaphors in its basic vocabulary. We speak of rising and falling melodies, of heavy bass lines, and soaring soprano arias. Musical tension and resolution mirror the physical tension we feel when lifting something against gravity and the release when we set it down. Rhythm itself, the foundation of music, often reflects the natural cadences of walking, running, or heartbeats, all processes shaped by our gravitational environment. In literature, Gravity provides powerful symbols and metaphors. Flight represents freedom, transcendence, or escape from earthly constraints. Falling symbolizes moral failure, loss of control, or a return to harsh reality. The weight of objects often stands in for emotional or psychological burdens. These motifs appear across cultures and periods, suggesting again how deeply gravity has shaped our symbolic imagination. Perhaps nowhere is gravity's influence on human thought more evident than in our concept of groundedness. To be grounded is to be stable, realistic, connected to fundamentals. We speak of grounding our arguments in evidence, of finding our ground in shifting circumstances, of the ground of being in philosophical discourse. This language reflects a deep recognition that gravity provides the literal ground beneath our feet, the foundation upon which all human experience rests. The opposite of groundedness, weightlessness, carries complex associations in human thought. It can represent freedom from constraint, a transcendence of earthly limitations, but it can also signify disconnection, disorientation, a loss of reference points. Astronauts who have experienced actual weightlessness often report mixed feelings, a sense of liberation combined with a profound longing for Earth's embrace. This ambivalence toward weightlessness appears throughout human culture. In religious mysticism, spiritual experiences often involve sensations of floating or flying, a liberation from physical constraints that mirrors the soul's freedom from earthly concerns. Yet these same traditions typically emphasize the importance of returning to earth, of grounding spiritual insights in compassionate action and embodied practice. Our sense of time itself may be influenced by gravity. The rhythms of days and seasons, the cycles that have structured human experience throughout our evolution, all depend on gravitational relationships, the spinning of Earth on its axis, its orbiting of the Sun. Our internal body clocks, evolved in response to these gravitational rhythms, influence not just our sleep cycles but our emotional patterns, our sense of time passing quickly or slowly, our experience of life's pace. What would happen to the human mind, to human culture and meaning, if gravity were to disappear? Beyond the physical catastrophe we've explored in earlier chapters, we would face a profound conceptual and emotional disorientation. Many of our most basic metaphors would lose their experiential foundation. The spatial organization that underlies so much of our thinking would be undermined. The very concepts of up and down, high and low, rise and fall, would become arbitrary without gravity's orienting influence. Language itself might need to evolve to capture the new reality of a gravitationless existence. New metaphors would emerge based on different physical experiences, perhaps related to momentum, inertia, or the properties of objects in contact. But the transition would be jarring, requiring a fundamental rethinking of conceptual frameworks that have shaped human thought for our entire existence as a species. Art and aesthetics would undergo similar transformations. Dance in zero gravity would bear little resemblance to its earthbound predecessor, perhaps becoming more akin to three-dimensional sculpture, with bodies moving freely in all directions, without the constraints or expressive possibilities that gravity provides. Architecture would lose the tension between structural necessity and artistic vision that has driven its evolution. Music might shift away from rhythms influenced by walking or heartbeats toward patterns based on different physical experiences. Our emotional vocabulary too would require revision. What would sadness mean without the embodied experience of heaviness, of being pulled downward? How would we conceptualize joy without the sensation of lightness, of rising up? Even our understanding of moral struggle might need rethinking without the physical experience of resisting gravity's downward pull, as a metaphor for resisting temptation or base impulses. Yet human creativity and adaptability should not be underestimated. Given time, a gravitationless humanity might develop entirely new conceptual frameworks, new metaphors drawn from their altered physical experience. Momentum and inertia might replace weight and lightness in the emotional vocabulary. The experience of tethering oneself to prevent drifting might generate metaphors about connection and disconnection, replacing those based on rising and falling. The three-dimensional freedom of movement might foster thinking less constrained by hierarchical models, as up would no longer be privileged over down. Of course, our scenario does not allow for such adaptation. The disappearance of gravity would, as we've explored, lead swiftly to the end of human existence, along with all other life forms. But this thought experiment nonetheless reveals how thoroughly gravity has shaped not just our physical existence, but our conceptual and emotional lives. Perhaps the most profound insight this exploration offers is how deeply our sense of meaning is embodied, rooted in physical experiences that we seldom consciously consider. Gravity is not just an external force acting upon us, but has become internalized in our thinking, woven into the very structure of our minds through evolution, development, and cultural transmission. It has shaped not just what we think, but how we think. This recognition connects to philosophical traditions that emphasize the embodied nature of human cognition, from phenomenologists like Maurice Merleau-Ponty to contemporary cognitive scientists like Antonio Damasio. Thinkers have increasingly recognized that the mind is not separate from the body, but emerges from bodily experience in a physical environment, an environment fundamentally shaped by gravity. There is something humbling in this realization. The force that keeps our feet on the ground also shapes our highest thoughts, our most abstract concepts, our sense of meaning and purpose. Our souls, if we may use that term for our deepest sense of self and meaning, are not separate from the physical universe, but emerge from our embodied existence within it, an existence fundamentally conditioned by gravity. Yet there is also something elevating in this perspective. It suggests a profound continuity between the physical and the metaphysical, between the forces that shape galaxies and those that shape our thoughts. In understanding gravity's role in human meaning, we glimpse how we are not separate from the cosmos, but intimately connected to it, our inner lives reflecting the same principles that organize the universe at large. This perspective offers a kind of cosmic belonging, a recognition that our subjective experience is not alien to the objective universe, but emerges from it and reflects its nature. The same force that holds stars together holds meaning together in our minds. The same principles that organize planets around suns organize concepts in our thinking. We are, in a very real sense, the universe becoming conscious of itself, and gravity is a thread that runs through both the cosmos and consciousness. What does this tell us about the human soul? Not the traditional concept of an immaterial essence separate from the body, but the soul understood as our capacity for meaning, value, and transcendence. It suggests that this capacity does not stand apart from the physical universe, but is continuous with it, emerging from the same principles and processes that shape the cosmos at large. This does not reduce the soul to mere physics. Rather, it elevates physics to something that can give rise to meaning. It suggests that the universe is not merely matter in motion, but has woven into its very structure the potential for consciousness, for significance, for what we might call soulfulness. Gravity, in binding matter together into complex structures, creates the conditions for mind to emerge from matter, for meaning to arise from mechanism. And so we find, in this exploration of gravity and the human soul, another remarkable connection between the cosmic and the personal. The same force that shapes galaxies shapes our thoughts. The same principle that organizes solar systems organizes our concepts. The same relationship that binds planets to stars binds metaphors to meanings in our minds. Without gravity, we would lose not just our physical grounding, but our conceptual and emotional grounding as well. We would lose not just our world, but our way of making sense of any world. In this recognition lies a profound appreciation for the unity of existence, for the intimate connection between the forces that shape the universe and those that shape our inner lives. Gravity, it seems, grounds not just our bodies, but our souls. Our journey through a universe without gravity draws to a close. We have witnessed Earth come undone, seen the solar system unravel, watched galaxies dissolve, and contemplated the profound implications for space-time itself. We have considered what gravity's absence would mean for life, for consciousness, and even for the human soul. Now, as we return to the reality in which gravity remains our constant companion, we carry with us a deeper appreciation for this invisible force that shapes our existence in ways both subtle and profound. Imagine, for one final moment, the ultimate fate of our thought experiment. Billions of years have passed since gravity vanished. The former universe has become an ever-expanding void, growing emptier with each passing eon. The matter that once clustered in galaxies, stars, and planets has dispersed to near uniformity. Atoms and molecules drift in isolation, their encounters growing increasingly rare as space stretches between them. No stars shine in this darkness. Their fusion fires, once maintained by gravitational compression, extinguished long ago. No planets orbit, no galaxies spiral. The cosmic structures that gravity patiently built over billions of years have unraveled completely, leaving only the most elementary particles scattered across an immensity of empty space. If consciousness could somehow observe this scene, it would witness a universe profoundly different from the one we know. No discernible direction exists without gravity's guidance. No up or down, no center or periphery. The fundamental asymmetry that gravity introduced into space, creating wells and gradients that drove cosmic evolution, has disappeared. What remains is nearly perfect uniformity, a cosmos approaching maximum entropy, the heat death that may be the ultimate fate of our actual universe, but reached far sooner without gravity's organizing influence. Light still travels through this void, but with less and less to illuminate. The electromagnetic force still operates, occasionally causing atoms to form molecules when they happen to drift close enough. The strong and weak nuclear forces continue to bind quarks into protons and neutrons, and these into atomic nuclei. But without gravity to gather these basic building blocks into larger structures, they remain just that, building blocks with nothing to build. Time itself grows less meaningful in such a universe, with no cyclical processes like planetary rotations or orbits, no biological rhythms, no complex systems evolving through states of greater or lesser order. Time becomes merely duration without distinction. Each moment resembles the one before and the one after. Change still occurs, but it is the small random change of particles drifting and occasionally interacting, not the directed change of evolving complexity. In this distant future of our gravitationless cosmos, even the concept of location becomes increasingly meaningless. Without reference points, without structures to measure distance against, position becomes purely relative. With no gravitational wells to create space-time curvature, space flattens into perfect uniformity. The rich topography of our current universe, with its hills and valleys of warped space-time around massive objects, gives way to an endless, featureless plane, stretching in all directions. Temperature, too, approaches uniformity throughout this cosmos. Without gravity creating the pressure needed for stellar furnaces, no new heat sources emerge to replace those that faded long ago. Energy, once concentrated in stars and other compact objects, has dissipated across the expanding void. The temperature gradient that once drove weather on planets, convection in stars, and countless other processes no longer exists. The universe approaches a state of thermal equilibrium, neither hot nor cold, but lukewarm throughout, unable to perform work or drive complexity. In our current universe, gravity creates pockets of order that temporarily defy the trend toward entropy. Stars, planets, and living things represent local decreases in entropy, temporary islands of organization in a cosmic sea trending toward disorder. Without gravity to create and maintain these islands, entropy reigns unchallenged. The arrow of time points more relentlessly than ever toward increasing disorder, with no countervailing force to create even temporary reversals of this trend. The atoms that once formed your body, the carbon and oxygen and nitrogen and all the rest, now drift alone or in simple molecular combinations, separated by vast gulfs of empty space. The particular arrangements of these atoms that constituted your physical form, your memories, your sense of self, dispersed eons ago, within the first moments of gravity's disappearance. Yet the matter itself persists. The fundamental particles neither created nor destroyed, but merely rearranged and scattered across the cosmos. This dissolution represents not annihilation, but transformation. The universe has not ceased to exist, but has changed its nature fundamentally. From a cosmos organized around centers of mass, with matter gathered into distinct structures at nested scales, from particles to superclusters, it has become a nearly uniform expanse with matter distributed almost evenly throughout space. The symphony of complex interactions that characterized our universe has faded to an occasional, random note sounding in the darkness. There is a strange peace in this imagined future. The ceaseless struggle against entropy, the constant work of maintaining order against the tide of disorder, has ended. No stars labor to fuse hydrogen into helium. No living things strive to preserve their complex organization against the trend towards simplicity. No conscious minds grapple with the mystery of existence. All has returned to a state of elemental simplicity, not unlike the very early universe before gravity had time to create distinction and structure. But what of the other forces? Electromagnetism, the strong nuclear force, and the weak nuclear force continue to operate, maintaining what little structure remains. Atomic nuclei stay intact, held together by the strong force. Electrons continue to orbit these nuclei, bound by electromagnetic attraction. Occasionally, the weak force mediates the decay of certain particles into others. These processes continue, but without gravity to gather matter into sufficient densities, they rarely lead to complexity beyond the molecular level. In a sense, our thought experiment has taken us full circle, from a universe rich with gravitational structure to one resembling the very early cosmos before gravity had time to work its organizing magic. In the first moments after the Big Bang, matter was distributed almost uniformly, with only tiny fluctuations in density. Gravity amplified these fluctuations over billions of years, creating the cosmic web of filaments, clusters, galaxies, and stars. Without gravity, our universe would return to a state somewhat resembling its beginning, though ever expanding and cooling rather than compressed and hot. This is the cosmos without its architect, the universe without its principle of relationship. It is a place of isolation rather than connection, of dispersion rather than gathering, of simplicity rather than complexity. It is a universe that has lost its ability to know itself through the emergence of structured matter capable of consciousness and contemplation. And yet, even in this bleakest of scenarios, something remains. The potential for complexity, though unrealized, still exists in the laws of physics themselves. The particles drifting through the void still carry the properties that, under different circumstances, allow them to combine into atoms, molecules, stars, and eventually thinking beings. The story has ended, but the alphabet from which it was written persists. In this sense, our thought experiment reveals not just the importance of gravity, but the resilience of possibility itself. Even in imagining the most profound disruption of cosmic order, we cannot truly conceive of absolute nothingness or the complete cessation of potential. Something abides, even if only the most basic constituents of reality and the laws that govern their behavior. This persistence of potential offers a strange comfort as we return from our imaginative journey to the reality we actually inhabit. For if even the most catastrophic scenario we can envision cannot entirely eradicate the foundations of existence, how much more secure is our actual universe, where gravity continues its patient work of building complexity from simplicity, structure from uniformity, relationship from isolation. The gravitational universe we inhabit is not static but dynamic, not ending but evolving. Gravity continues to form new stars from interstellar clouds, to shape new planets around these stars, to guide the complex dynamics of galaxies and clusters. The cosmic story continues to unfold, with gravity as its principal author, creating the conditions where matter can organize itself into ever more complex forms, including forms capable of contemplating their own origins. As we lie here on the threshold of sleep, our bodies gently pressed against the bed by the same force that holds the moon in its orbit and binds the Milky Way together, we exist at the intersection of the cosmic and the intimate. The pressure we feel is gravity's quiet reminder of our connection to everything that exists, from the smallest grain of sand to the most distant galaxy. We are held in a universal embrace, participants in a relationship that spans the cosmos. Perhaps there is a lesson in this recognition, a wisdom that emerges from our thought experiment. By imagining the absence of what we normally take for granted, we awaken to the gift of what is. Gravity, in this light, appears not as a limitation to be overcome, but as a condition that makes possible all we value, all we know, all we are. Its constant presence, so ubiquitous that we rarely notice it, reveals itself as precious, precisely through our imagining of its absence. In our actual universe, unlike our thought experiment, gravity maintains the conditions for an ongoing cosmic story. Stars will continue to form and shine for trillions of years. New planets will coalesce around these stars. Life may emerge on countless worlds, evolving forms we cannot imagine. Consciousness may arise again and again, bringing the universe to awareness of itself in endlessly varied ways. All of this ongoing creativity depends on gravity's patient gathering together of matter against the expansive tendency of space itself. Even in the far future of our actual universe, when the last stars have burned out and galaxies have dispersed beyond each other's horizons, gravity will continue its work on smaller scales, maintaining structure and relationship. Black holes may become the last bastions of organized matter, slowly evaporating through Hawking radiation over timescales that dwarf the current age of the universe. Through it all, gravity remains, holding what it can against the tide of cosmic expansion. In our brief moment in this ongoing story, we have achieved something remarkable. We have come to understand, at least in part, the force that shapes us. We have recognized our place in a gravitational cosmos, our participation in its evolution, our embodiment of its principles. We have developed the capacity to imagine gravity's absence, and through that imagination, to appreciate more deeply its presence. As you drift towards sleep, feeling the gentle pressure of your body against the bed, the subtle pull of Earth beneath you, remember that this sensation connects you to the entire cosmos. The same force that holds you now shaped the stars that forged the elements in your body, gathered the matter that formed our planet, and created the conditions where life could emerge and evolve. You are held in an embrace that spans the universe, a relationship that has persisted since the earliest moments of cosmic history. And so we end where we began, with gravity as the silent architect of existence, the force that holds everything. In its patient gathering together of matter against the tide of cosmic expansion, gravity has created the stage upon which the drama of life and consciousness unfolds. Without it, we have seen, nothing we know would be possible. With it, the universe continues its remarkable journey, from simplicity to complexity, from uniformity to diversity, from unconscious matter to conscious contemplation. The stars will continue their courses, the planets will maintain their orbits, the galaxies will spiral through space, and we, children of gravity, will remain grounded in the cosmos that shaped us, held by a force we may never fully understand, yet could never live without. And so, the universe would drift, without direction, without time, without gravity. But tonight, we remain grounded, held by a force we may never fully understand, yet could never live without.